Take a deep breath and dive into an unforgettable experience.
University of Porto sits in the top 1% of the world's universities, internationally recognized by the quality and depth of its teaching and research. As a comprehensive university, we offer courses in all study areas and all levels of higher education, from undergraduate to postgraduate programs. Reasons more than enough to be the preferred university in Portugal by national and international students. A community of more than 30,000 that choose the University of Porto to develop their career path or a research project. We stand out as the largest producer of science in Portugal, authoring 25% of all the scientific papers published every year. In our research units, you may find some of the most productive and renowned European R&D centers. Consequently, the University of Porto is a driver for innovation, helping students and researchers turn ideas into new products, services, and companies. Hundreds of startups and thousands of new jobs were created in our premises, affirming Porto as one of the most innovative regions of Europe. Moreover, all this is done in one of the most beautiful regions and cities of the world, voted as Best European Destination. The city of Porto is itself an attraction, booming with life and culture. And we, at the University of Porto, would welcome you with open arms.
How many times have you left early, cancelled a meeting, or otherwise changed your plan? How many times have you said you were going, but stayed right where you were, sinking in the sand? How many times did you look at yourself from another perspective and grasp, when all was said and done, you were simply in the wrong place? Listen, we're the same size as what we see and not what we have. A man needs to see things with his own eyes, walk the world with his own feet, have his back burned by the sun and his feet blistered by the street. Which is harsher, the icy winds atop a mountain or the baking heat along the plain? There's only one way to know, seeing this with our own eyes and not on our smartphones, flashing up images of landscapes already shared 1,000,000 times, really seeing with our own gazes for just a few and sometimes far too few times. The good news is they are still here. These landscapes do persist in the three-dimensional world that we exist, and they do hold the capacity to transform us. So come, take a look, but look to see and not to show, and save it right here and here. Put the phone away and go. Once we experience distance, we understand just how much we miss our own and our homes. We can see the wood from the trees. Travel helps us flourish and grow. We need to go places we don't know to shatter that arrogance that makes us experts in what we have not seen, when we should remain humble and keen as students and just head off in discovery. In 20, 30, 40 years' time, we're going to regret what we did not do. So voyage out, let the wind blow through your sails, explore, dream and discover. Believe that that sky is going to seem that bit bluer. You must have read, when something good happens, travel to celebrate. When something bad happens, travel to forget. And when nothing happens, travel to make something happen. Keep this in your head. It's the truth. And this is the proof. And it's with us each and every day. We just have to read the signs. Because after all, We can't skip life. How many times have you left early, cancelled a meeting, or otherwise changed your plan? How many times have you said you were going, but stayed right where you were, sinking in the sand? How many times did you look at yourself from another perspective and grasp, when all was said and done, you were simply in the wrong place? Listen, we're the same size as what we see and not what we have. A man needs to see things with his own eyes, walk the world with his own feet, have his back burned by the sun and his feet blistered by the street. Which is harsher, the icy winds atop a mountain or the baking heat along the plain? There's only one way to know, seeing this with our own eyes and not on our smartphones, flashing up images of landscapes already shared a million times, really seeing with our own gazes for just a few and sometimes far too few times. The good news is they are still here. These landscapes do persist in the three-dimensional world that we exist, and they do hold the capacity to transform us. So come, take a look, but look to see and not to show, and save it right here and here. Put the phone away and go. Once we experience distance, we understand just how much we miss our own and our homes. We can see the wood from the trees. Travel helps us flourish and grow. We need to go places we don't know to shatter that arrogance that makes us experts in what we have not seen, when we should remain humble and keen as students and just head off in discovery. In 20, 30, 40 years' time, we're going to regret what we did not do. So voyage out, let the wind blow through your sails, explore, dream and discover. Believe that that sky is going to seem that bit bluer. You must have read, When something good happens, travel to celebrate. When something bad happens, travel to forget. And when nothing happens, travel to make something happen. Keep this in your head. It's the truth. And this is the proof. And it's with us each and every day. We just have to read the signs. Because after all, we can't skip life.
The University of Porto sits in the top 1% of the world's universities, internationally recognized by the quality and depth of its teaching and research. As a comprehensive university, we offer courses in all study areas and all levels of higher education, from undergraduate to postgraduate programs. Reasons more than enough to be the preferred university in Portugal by national and international students. A community of more than 30,000 that choose the University of Porto to develop their career path or a research project. We stand out as the largest producer of science in Portugal, authoring 25% of all the scientific papers published every year. In our research units, you may find some of the most productive and renowned European R&D centers. Consequently, the University of Porto is a driver for innovation, helping students and researchers turn ideas into new products, services, and companies. Hundreds of startups and thousands of new jobs were created in our premises, affirming Porto as one of the most innovative regions of Europe. Moreover, all this is done in one of the most beautiful regions and cities of the world, voted as Best European Destination. The city of Porto is itself an attraction, booming with life and culture. And we, at the University of Porto, would welcome you with open arms.
Teste som.
On the western edge of Europe, where the land meets the sea and the winds carry the warm scents of Africa, there is a country of friendly and hospitable people. A country of contrasts, whose diversity is one of its greatest treasures. Of lands where nature has remained untouched and time appears to have stopped. A realm of endless plains and beaches washed by the Atlantic and caressed by the sun. Portugal, a country that needs to be deeply experienced to be understood. A country of artists whose works have made Portugal world-renowned. Its long history can be seen in its imposing castles, where we can spend the night within walls that have protected kings, caliphs, and the march of time itself. In fairy tale palaces, surrounded by enchanted forests, abundant with romantic walks and secluded areas. Where even those already in love develop new passions. But Portugal has also another facet, where the grandeur of the past and the excitement of the future live side by side. A young and welcoming nation that lives intensely 24 hours a day. A vibrant country full of color, where the sun shines all year round. In mountains that can take the breath away from even the most experienced traveler. In places where the grandeur of the landscape is rivaled only by the majesty of the fauna. And even when you think you have seen everything, Portugal has something more to offer. The possibility of doing nothing. Relax and enjoy the endless beaches of a country with 850 kilometers of coastline. After a busy day, start your evening with a great meal. Because in a country with centuries of history and some of the best wines in the world, cooking has become a highly appreciated art. Portugal is all this and much more. A marvelous and captivating country from the very first moment you arrive. A unique country that offers 1,001 things to do. Embark on an exciting journey. Take a deep breath and dive into an unforgettable experience.
Essaie de bâtir, de structurer ça. La bêtise, c'est un paresse. La bêtise, c'est un type qui vit et il se dit ça me suffit. Il se donne pas le coup tous les matins en disant c'est pas assez. Je ne sais pas cette chose, je ne vois pas cette chose, je ne sais pas cette chose. C'est la paresse, on voit la bêtise. qu'un certain nombre d'individus ne peuvent pas t'encaisser. C'est très moral, c'est très normal. Alors, je ne dis pas que ce soit plaisant, mais c'est pas la fin du monde.
Mesdames, Messieurs, bonsoir, c'est Patrick Poivre d'Arvor, vous écoutez Bon Entendeur.
Good morning, everyone. I hope you can hear me well. Yeah, it is connected. Is everyone hearing me well? Hello? Good morning.
Good morning, but the sound is very low.
Very low? Maybe if I... So if I speak like that, is it better?
It's better. Thank you.
Thank you, Philippe. Good morning, everyone. Welcome to the second day of SBAC-PAD 2020. I will be chairing this first session of our second keynote speaker, first actually, second, Frank was speaking yesterday. So it's my pleasure to introduce you to Brice Goglan. And please tell me, Brice, if I'm pronouncing your name correctly. My French is not very good, so not good, no, it's nothing actually. So
yeah, it's okay.
So Brice's main research interest is on memories of several different levels, hierarchies of memories and the heterogeneous systems. And his main research achievement recently is this library called HWLOC. That's the portable abstraction of the hierarchical topology of modern architectures, including NUMA, memory nodes, sockets, shared caches, cores, and simultaneously multi-threading. But besides his outstanding research work, Brice also spends his time disseminating knowledge on physics and informatics in his blog. Actually, he's got a blog. And he also has some interesting things. I wanted to show you a picture here. I don't know, here, should be here. He's got a very good sense of humor. And yeah, so I think I'm not in Zoom. Anyway, if you go to his webpage, you see some very nice picture, cartoon. I don't know if this is authored by him or not, but he can talk about that. Daniel is trying to help me here with the, I don't think I have Zoom.
Yes, you are on Zoom.
Am I?
Yes. I'm seeing in Zoom. Okay, come on. Sorry.
Shall I join? No. Well, I don't want to delay any further. If you go to his webpage, he's got a very nice cartoon about, you know, this Frankenstein with 120K of memory and some new technological stuff implemented on it, anti-incontinence stuff. So have fun. Brice, go ahead. Thank you very much.
Thank you for the introduction. Can you hear me? I cannot share my video. It says
No.
I'm not allowed.
We can see you.
Okay. Can you see the slides?
Yes, it is okay.
Okay, good. Okay, so thank you for the introduction. So yeah, I'm going to talk about task and data placement, multi-cores, and all these crazy things we have in modern parallel architectures. I've been working on that for more than 10 years, so there are a lot of things to do. So I'll try to focus on interesting remaining pieces. So the plan is to, after a brief introduction, I will talk about how we model the architecture, and I will soon talk about the fact that we model it in a hierarchical way because it's very convenient. I will explain that. So how do we model the architecture and how do we perform task placement on top of that? Then we will talk about this hierarchical modeling. Is it okay? Is it enough? Should we break it for some reason? Spoiler, the answer is basically no, except for some cases. Then we'll talk about what programming models and standards are doing for all this, because I'm working in a small library that is just at the bottom of the stack in your software layers. But at the top of the stack, you have applications with programming models, and they need to be able to use all this information. And I will talk about what they are actually doing to use that. And then we'll talk about heterogeneous resources, including CPUs and memories. So let's start with an introduction. So first, all of you know that the machines are very complex these days. We have usually in servers multiple processors. So what I call packages or socket or CPUs is basically the same. It's what you put on the motherboard. So the actual name these days is a package, but it's the same as a socket or a CPU. We have mini cores in these packages. We have lots of caches, which are organized in a hierarchical way. So usually you have some private caches for every core, and you also have some shared caches between all of them or between part of them. You also have some GPUs or accelerators, some network interfaces, InfiniBand, and things like that. And nowadays, we also have some heterogeneity, like different kinds of memory or maybe different kinds of CPU cores. So this is very important because if you want to make the most of the architecture, you need to be aware of some details, not all the details, but at least some of it. Otherwise, the performance won't be good. So topology matters to performance. So if you take this random machine, which is made of 2 packages with 2 NUMA nodes each and 4 cores, so a total of 16 cores, if you measure the performance by doing, for instance, of MPI benchmark from one core to another, you will get some low latency and some kind of bandwidth. We don't care about the numbers. Then if you go to a core that isn't as close as the first one, you will get some lower performance, usually a bit higher latency and lower bandwidth. If you go to another package in the same machine, the performance will decrease again. And if you go to another machine, the performance will decrease again because you have to go across the network between the machine, etc. So if you're going to communicate between some tasks, those tasks should rather be close physically, so on neighbor cores. Otherwise, the performance will be lower. It's not strictly required, but it's better for performance. So task placement matters to performance because of this. So this matters for MPI, for communication performance, also for non-MPI things. Usually the bandwidth is going to decrease with the physical distance and the latency is going to increase. I say usually because sometimes you have some strange hardware characteristics that doesn't change the performance in some cases, but usually it goes like that. Performance is lower when the distance between the tasks increases. That's true for communication, but it's also true for memory sharing or synchronization. So if you have some OpenMP threads that communicate by having one thread write in memory and another thread read that memory or do some synchronization like barriers, if they share a cache, it will be fast because they are close and the cache is going to make those data transfer very fast. If they don't and they are across the entire machine, it will be slower. So process placement, it's actually 3 problems. First, you have to understand what the application tries to do. Does it try to communicate between this piece and this other piece of the application and things like that? Does it synchronize, etc.? Then you have to model the architecture, which is what I'm going to talk for most of this presentation. How is the hardware organized? How many cores do we have? Which one are close to each other? Which one are far away? Is the memory close to this core or this other core, etc.? And once you have the model of the application and the model of the architecture, you basically want to map one onto the other so that the software affinities that you have, for instance, 2 tasks that communicate a lot, you're going to map them on some hardware affinities like 2 cores that are close to each other. When you do that, you will get some performance improvement because if latency is lower between 2 tasks, communication will be faster and the application will be faster. You might also get some productivity gains because if you model the application and the architecture very well, you might be able to place the task automatically very easily. And then when you switch to another machine, you just remodel the new architecture, you redo the mapping, and you get the best placement automatically. So in the end, you don't have to retune your application for every machine just because you modeled the application once, and then you just have to model the architecture again, and it works. So let's talk about modeling the architecture for real now. So all of this started more than 10 years ago. So we had lots of people complain about this. Basically, they buy a new machine, they look at how the cores and memory are organized, and then they try to place their task on this machine. So again, if some tasks are going to work together, they will place them on neighbor cores. They're going to allocate the memory in the local memory, in the memory that is local to these cores, and they get some performance that is okay for them. Good. Then one machine in the cluster is going to die for a random reason. So the vendor comes and replaces the motherboard, and then you run the application again, and the performance is not good anymore. So what's going to happen is that basically you have some different nodes for some reason, and you're going to have to change the placement of your task depending on which node you use, just because the one was modified, was physically modified. It's actually the same problem if you have your application running on a cluster, you have another cluster in another data center, you're going to have to modify your application placement on this new cluster because the core are not organized the same. Even if the processors are similar, you still have to modify your data placement. So it's not very convenient because you try to tune your application, but you have to modify it basically every time you switch from one cluster to another, or sometimes even inside the same cluster because some nodes are slightly different. So what happened here is that basically the new motherboard on the node that had an issue came with a new BIOS release, and sometimes the BIOS is going to change the way the resources are indexed. So for instance, two processes running on core 0 and 1, in the previous revision of the BIOS, they will be actually running on cores that are neighbors physically, but now it's not the case anymore because the BIOS decided to number the core in a different way. Why would it do that? The reason is that vendors, so people like Dell, HP, or whatever, they decide how to number the resources in the machine. And there are some reasons for numbering the resource in a way or in another. For instance, if you decide that core 0 is local to the first NUMA node and core 1 is local to the second NUMA node, it will be better for memory bandwidth because if you don't do anything for your application, so you just come with your application and you just run it without any optimization, the first task will go to the first core, the second task will go to the second core. So both of them will have a local memory only for them. So overall, the memory bandwidth will be higher just because they use different memory. It's not good for sharing, but it's better for the overall memory bandwidth. So basically, the vendors, they have to decide how to organize the resources, and they try to guess one numbering that will be good for dumb applications that are not optimized. Another thing they do is, for instance, they put the hyperthreads at the end of the list so that you don't use them by default because hyperthreading causes some issue. So basically, they have to number the resources in some way, and they try to find one that could help applications that are not optimized. Of course, sometimes it's wrong. Sometimes they change their mind, and every time they release a new product, they have to update that because the CPU is different, etc. So sometimes you buy a product, the resources like the core will be numbered in a way, and then you upgrade the BIOS and the numbering change because they fix things or they change their mind on how to do that. And that's the big issue because it means that whenever you upgrade the BIOS on a machine by changing the motherboard, basically, you might get some performance changes because of that. So that's why we created HWLock in the beginning. So HWLock, it means hardware locality. It's a project that we have been working on for more than 10 years. So what we did in HWLock, one of the main feature in the beginning is that we try to renumber the resources in a logical way. We don't want to have what we call physical indexes. So basically the way the hardware of the operating system number resources, we don't want that to change anymore. We want a logical numbering of resources. For instance, core 0 is going to be close to core 1, always. In the hardware, it's not true because the number is different. Core 0 and core 1 could be somewhere else. But at least in our software, it's not going to be the case. So what we want is that whenever you upgrade the BIOS or you change the operating system or you buy a machine that is slightly different, etc., we still want the numbering of resources to be logical, which is basically it's something very convenient for applications. If you want two cores that are close to each other, take core 0 and core 1, you'll be sure they are close to each other. So we want to be portable across hardware and software platforms. So this feature was a very simple idea, but actually it was very useful to users because they didn't have to care anymore about which BIOS or operating system or whatever version is running. They will just use the logical ordering that we give them, and it works. So since then, we've been trying to convince users to use that, and it's not easy. So basically, we're telling users never bind your task using the physical numbering. So what's in the hardware, and that one changes from time to time. So if they really know what they are doing, they could use this physical numbering, for instance, when debugging specific things. But in general, don't use that in your application because you will have to deal with the portability issues. Use our logical numbering instead, and it will be much easier for you. But it takes time. We've been working on convincing users for a while. So why is this not solved yet? It's been 10 years, and HWLock is used in a lot of runtimes now. The problem is that people have been dealing with these issues for years. So they develop their own custom scripts, etc. So if their script works, why would they spend time porting their code to HWLock instead of using their script, which works? They want to be convinced that it works better. They want to be convinced that HWLock will work with new CPUs. Also, it looks like a black box to them, so some people don't like that. So they want to check that it's actually working at what it's actually doing. And also, if there's ever a bug in our code, they will have to go back to their script. So all of this means that it took a lot of years before people actually stopped using these non-portable physical indexes and starting using our logical indexes. And actually, a couple of weeks ago, I received an email from somebody working at the Praise Summer of HPC. So I'm not sure how it exactly works, but basically they hire some kind of engineer or intern during summer because they had to fix some issue. And if you look at this issue, it was basically a big European computing center still using some very old option in OpenMPI, which has been deprecating for years. They were basically saying, I want to pin my task to the specific cores using physical index. And of course, when they switched to a new ARM system, it broke because physical indexes were different, because this machine is very different from what they usually had. So the intern developed a new software. I told them, no, stop using this CPU set things. Just use what OpenMPI provides nowadays. It will use HWLock and everything will work. So still 10 years ago, still some people using some old things and having problems that should not exist anymore. So why are all these things actually so complicated? The problem is that process placement isn't easy. There are a lot of policies. There are policies for mapping, ranking, and binding. I'm not going to explain everything, but basically you need a way to select where you're going to place some processes, in which order you're going to select these resources, and then you're going to select how many cores you're giving to each process that you bind to these resources. So when you combine all these policies, you get lots of different use cases. Many of them are valid, and it makes the overall use of this MPI binding policies very complicated. For instance, if you're doing MPI plus OpenMP, you have to specify how many MPI ranks you want, and then how many OpenMP threads you want in every MPI rank. And when you deal with all this combination of layers of runtimes, things become very complicated. So MPI implementers work on that for years. They now support a lot of options, but of course, options are slightly different from one MPI to another. Also, the default binding policy might be a bit different from one MPI to another. Sometimes they have some special cases that triggers for some cases, which basically makes the things very complicated to understand. So when people try to place their processes, at least for MPI, it's very difficult to understand everything that's going on. So that's why also they still use their custom script to actually verify that MPI is doing what they want. So why don't we just do this? Well, the first thing is that in the MPI standard, you have standardization of the MPI programming API, but you don't standardize MPI run and MPI exec options. It's something that may change in the future, but right now there's nothing like that. So basically, you have the entire API that is portable for different MPI, OpenMPI, MPitch, Intel MPI, whatever. But the way you launch the application might be different because MPI run and MPI exec and maybe srun too use different options. So basically, when you try to do some process placement and you switch from one machine to another, and one is OpenMPI and the other one is MPitch, you have to spend time changing the options that you gave to bind your processes. So of course, it's not convenient. So some people started working on putting some portability for that. So I gave two examples here, like MPI pin and liquid MPI run, which try to do something portable across the different API, which is very good because once people know how to use these tools, it just works on the vast majority of clusters, at least all clusters that support one API that is supported by these tools. But of course, when you add a new standard on top of existing standard, you basically end up, well, it's not a standard, but it's a way to run MPI run. We add some existing MPI run option, and we're adding some new ones on the side, which might be a problem in the end. It will be good to actually standardize that instead of just adding another one on the side, because it's different. It's portable across different MPIs, but it's still a different syntax in the end. So at least on the MPI side, things work, but it's not very easy to use because there are a lot of different policies, and the way to use them is very different and non-portable. So now let's go back to the modeling of the architecture and how we actually place tasks on that. So what we do is we build a hierarchical tree of the resources. So we look at the machine. It contains different CPU packages, which contain, in this case, 2 NUMA nodes. So it's basically some memory. Each NUMA node has a L3, which contains, it's not really contained, but it basically works when we say inclusion or containing. So each L3 is associated to different L2, which are associated to L1 and cores. And then at the bottom, we have what we call PU, which is a processing unit. It's basically an hyperthread. So we build a hierarchy of these compute resources by saying we group the object by core and then packages, etc. And when there are some caches or NUMA node attached to this set of core, we put it in the hierarchy as well. So it's what we call a structural modeling. It's structural because it means it says how things are organized, but there's nothing about performance. That I will talk about that later. But basically, you don't say here that L2 is faster than L3, for instance. You just say things are organized like that. So when we started doing that 10 years ago, people did not expect to get that many information, actually, because in the past, people knew they had a certain number of cores, maybe some packages containing their cores, but they did not expect that many information. So right now, if you look at the previous, if you look at this slide, we have a hierarchy that is made of, I don't know, maybe 8 different levels, which is a lot. So when people have to use that, they have to figure out which level is actually important for them. The core is usually important because that's where you put an OpenMP thread or an MPI rank or whatever. But for intermediate level, it's not that easy. So there are some levels that are usually useless. For instance, L1 and L2, there's only one per core, so you don't really care about that from the hierarchy point of view. The size of these caches might be useful if you want to optimize your tiling, for instance, but the actual fact that there's a core is not useful because there's a single cache per core. Also, for each package, sometimes you have a single L3 or a single NUMA node. So in that case, which it was actually the case in a lot of platforms in the past. So in that case, if you decide to use, I don't know, one MPI process per package, it's the same as using one MPI process per NUMA node or per L3. So lots of people, they didn't understand all the details, but they knew that a package is a set of what core is. So they started using these 2 levels by default, which means when they started doing MPI plus OpenMP, they will put one MPI process per CPU package and one OpenMP thread per core. And it worked very well for several years. The problem is that in the recent years, things started breaking. The reason is that processor architects, so people from Intel, etc., they like changing things. They have good reasons for doing that, but it wasn't very good for us. So for instance, now, when you have a CPU package, you don't have a single NUMA node in there. You actually have multiple NUMA nodes, so which means some cores of the package are close to some local memory, while other cores in the same CPU package are close to some other memory. So basically, if you bind your task to an entire package, it doesn't mean you're going to bind your task to a single NUMA node. You're actually going to use 2 of them, which might not be what you want. Sometimes also the L3 is not similar to the new node anymore. The reason is that on Intel recently they started having large caches that cover the entire package, while the NUMA node is still half a package. So if you bind to NUMA node, it's not similar to binding to L3. So it really depends what you want to do. And on AMD, it's actually even more complex than that, because in each package you have several NUMA nodes, and each NUMA node contains several L3. So we have lots of hierarchy in there, and we have to decide where to bind. So if you are going to bind one MPI plus OpenMP process per package, is it really what you want nowadays? It's not clear, because inside that package you can still have some cross-NUMA remote accesses, because you have different NUMA nodes in the package. You can also have some inter-cache traffic, because you have multiple L3. So you need to take a step back and think about what do you want to use actually for your application. Do you want to have shared memory between all your OpenMP threads? In that case, you might want to bind your process to a NUMA node instead of the entire package, because two threads in the same package but running on different cores might not use the same NUMA node, because there are multiple NUMA nodes per package. If you want to do some synchronization, maybe you want to share a cache. So in that case, you might want to bind to L3 instead of a package. So it really depends what you want to do. So basically, process placement is becoming harder these days, because there are different levels, and you really need to understand what you want to do with your application. Do you want to optimize for shared memory or cache sharing or something else? And that's not easy for users. So basically, what we're saying to user is that you don't want to assume anything about the hierarchy. CPU vendors are going to change things in the future, like they did in the recent years. So some level might swap in the future, like L3 and NUMA. Sometimes L3 is larger than NUMA, sometimes NUMA is larger. It depends on the architecture. Some new level will appear. There are some processors with dies these days. There were some tiles and modules in the past too. It's not very clear what it means. It just means that some cores are grouped for whatever reason in the hardware. So don't expect to have only cores and package. You can have something in the middle, and make sure your application doesn't assume there's nothing in the middle. And of course, it will change. So you have to try to remain agnostic of all these changes. So basically, if you want to share some cache, you have to look at L3 and ignore the package and other things. So you really have to understand that the hierarchy might be very different from one machine to another. So what do we actually care about? We have a hierarchy that gives locality information. Even if we don't know that one level is made of package or NUMA or cache, we still have some information about the locality information. Basically, if you have two cores that are very close in the hierarchy, which means they are connected by a parent that is very low in the tree, basically, you know they are close to each other in the hardware, and you know that the performance between them will likely be good. You don't know exactly how better it will be than communicating between two cores across the entire machine, but usually it will be faster. So there's no quantitative information in this structural modeling, but there is some structural information which tells you if these cores are close to each other in the hierarchy, then the performance will likely be better. So thanks to this, we can do things like top-down recursive partitioning. So you have a set of data or a set of tasks to distribute across the architecture. You're going to start from the top of the tree, and then if you see that your machine contains two packages, you're going to split your task or data into halves, and then you're going to recursively do that again until you distribute things to the cores at the bottom. And you know that your task and data that you distributed like that, when they are placed on cores that are very close in the hierarchy, their communication or synchronization will be better. So how do we actually map a parallel application onto such a platform? So you want to figure out which tasks are going to communicate or synchronize or exchange a lot. And we want to place them together physically so that this communication, synchronization, or whatever is faster. So basically, you want to find the tasks that are very dependent to each other and place them in the hierarchy on cores that are close to each other. There are many tools to do that these days. There are things that are actually some generic partitioners. So they will basically take your application and split it in parts and then map it onto your hierarchy of resources. So Scotch, Metis, and Chicago are examples of that. Yeah. Is there a question or an issue? No. Okay. And there are also lots of specialized software now, like TopoMatch or LibTopoMap or MPIPP and many of them. So basically what they do, and if they take the hardware hierarchy, like what we built in the past, they will take the communication pattern of the application. So communication pattern can be different things. For MPI, it's explicitly the communication between MPI ranks. For OpenMP, it can be different things like how many data do I share with this guy. It could be also some more advanced things like the reuse distance when accessing some shared things. So there are lots of ways to define the communication pattern, but it's basically a way to measure the affinity between different tasks. So they take the hardware hierarchy, the communication pattern of the application, and they will give you a placement. So for MPI, it could be what we call a rank file, which basically says MPI rank 0 goes to core 3, for instance. For other runtime like Charm++ or OpenMP or whatever, it will tell you task number 3 goes to core number 4. And then you run your application, and the placement is better and performance should be better. So the communication pattern, how do we define that? It can be communication matrix. So on the right, you have an example. On the X index, you have basically a task number. It's an MPI rank in this case. On the Y index, it's also a task number. And basically, the black boxes means that, for instance, task 0 is going to send a lot to task 5. And when it's white, it means that these tasks don't exchange anything. So this communication matrix, which could also be a weighted graph, tells you how the application is organized, which tasks communicate a lot together and which tasks don't. So once you look at that, you can figure out that, for instance, task 0 and 5 in this case, they should be together. Actually, it's task 1 and 5 in this case. The way to measure the communication intensiveness between two tasks, there are different metrics for that. You can measure the number of messages. You can measure the total volume, so you aggregate the number of bytes exchanged between the tasks. You can also look at the average message size, because usually large messages contribute more to the performance changes depending on locality. So there are different metrics. I know some people working on that. It's not totally clear which one is better. It seems to depend on the application. But basically, you can use this kind of metrics to describe the communication pattern of your application. How do you get the application communication pattern? There are lots of runtime these days that can actually monitor the application and give you something that is similar to this matrix. You don't need very precise information. Just like the hardware hierarchy isn't very precise, you don't have performance information like bandwidth, for instance, in the hardware topology. You don't need precise information for the application communication pattern either. As long as the communication matrix has the good layout, you will be able to find out which task should be close together and which task can be far away in the topology. So I'm not going to detail more the communication, the mapping of this application on the hardware, but I can give you more detail if you have some question at the end. I know lots of people working on that. That's not the core of my work nowadays. So now let's talk about the model again. So we have a hierarchical model, which basically assumes that the machine is made of something that contains something else, etc. Is this actually true? Well, it depends. If you look at the NUMA interconnects, so for instance, here we have a machine with 8 Intel Xeon processor. If you look at the arrows between processors, you see that some of them are connected and some processors are not connected to other processors. So for instance, the one on the top left is not connected to the one on the bottom right. So it means the NUMA organization is not a complete graph. Some NUMA nodes are close to others, but not to some others. So this could be useful if you're really trying to improve to tune your application in depth. Some other NUMA interconnects are actually basically hierarchical. So this is an SGI platform. So I'm not sure SGI still sells some kind of machine like that, but these are very big machines with lots of cores, like up to thousands. And in this case, they are organized as boxes that contain multiple processors, and then you have boxes of boxes that contain multiple boxes, and then you have routers that are going to link different boxes, and then you have high-level routers. So you can still consider that hierarchical because you have your processors, some processor in the nearby box, some processor connected to the same router, and then some processors that are far away. So what we can do here is basically build some groups that are between the machine and the packages, which gives you an idea of how the machine is organized. And for people that really need lots of detail, we can give them the actual distance matrix if they really need that. It's not perfectly hierarchical, but it sort of works. But there are cases where things are not hierarchical. So this is a Broadwell CPU, so from, let's say, 4 years ago. We have 24 cores, if I'm counting correctly. And what we see is that these cores are actually organized on 2 rings. So it means that some cores are close to each other because they are connected on the same ring and they are close to each other on that ring. Some cores are on the same ring but far away, and some cores are on another ring inside the same processor. So this isn't flat, actually. So you cannot assume that all cores communicate as fast when they talk to different cores in the same processor. This is a Skylab processor now, and instead of 2 rings, we have a mesh with lots of tiles connected to them. So the way we model that currently in a JWLock is by splitting in 2 halves, because basically the cores on the left are connected to some memory. It's the gray part on the left. And the core on the right are connected to some memory. It's the gray part with DDR4 on the right. So basically, we split the cores into halves and assume that half of them are close to one half of the memory, and the other half are close to the other half of the memory. But it's not actually true, because some cores are very close to some memory, some in the middle are not as close, and also there are links between some core in the middle. So they are not actually split in half. It's just that we needed in some way, we needed a way to expose the fact that some cores are close to some memory and at least closer to some memories than to the other memory. So we decided to split it in half. Actually, it's not us, it's the firmware and Linux kernel, but we expose that the same. So this processor is not flat at all, but we're basically forcing it to be hierarchical, but assuming there's a separation in the middle. It's not perfect. Does it matter? Well, it's not clear. If you look in the literature, there are some people, like this example a couple years ago, where they try to optimize some runtime or application or whatever by looking at this ugly detail. So in this case, it was a Knight's corner, so it was the first generation of Xeon Phi from Intel. There's a ring connecting the cores inside the processor, and they figured a way to find out which core are close to each other on the ring, and then to optimize things because of that. But this kind of work is actually quite rare. So do we want to expose this kind of ugly details to the application? It's not clear. So my personal feeling is no, because if we add that many details to the model, basically things will become very complicated, and most of our users are normal users, are not hardcore users like the one I presented before. So we want to keep the model simple, even if we are doing some approximation. And also, if this kind of ugly detail were very important, many people will actually tune application for this detail, and they don't. We don't see a lot of articles like that in the literature. Also, lots of details about the hardware are not public anyway, so it will be very hard for us to expose this kind of detail in a precise and correct way. So we're assuming that the hierarchical modeling is correct, even if it's not perfect in general, but at least it works fairly well. So we don't want to break this hierarchical model. There are different reasons. The first one is that for algorithmics, it's very good. If you want to do some top-down recursive partitioning, so you have a set of data and tasks and you want to distribute them on the hardware by looking at the recursive hierarchy, it's very easy. You can do the same from the bottom to the top by basically starting from the bottom and grouping things by saying these tasks are on the same core, I'm going to group them, then I'm going to group by package, and then by machine, etc. And you can do all of this with good complexity because trees make algorithmics more simple than generic graphs. Also, this model is very convenient when you want to answer some questions that are very common when looking at locality, which is, for instance, what are the cores that are close to me? What is my local memory? Is there a GPU that is close to me? Is there a shared cache between two tasks, etc.? All these things are very easy to answer using the hierarchy. If we add a more complex model like a hierarchical graph, it will be more difficult. I'm not saying it will be impossible, but it will not be as easy. So now we talked about the actual nodes, so the servers, but when we do supercomputing, we have clusters or lots of nodes. So do we want to model the networks the same? So if you look at something like a fat tree, it's very easy to model in a hierarchical way. You basically say, I have some machine with their internal hierarchy. I'm going to group them by switch and then group them by the second level of switches, etc. This works very well. Once you have that, you have the entire hierarchy of the supercomputer, and you can perform process placement using the same methods like top-down recursive partitioning. It works well. The issue is that it doesn't work very well for all networks. For IB, it's okay. So for InfiniBand, usually you have some leaf switches where you connect the compute node. These are the switches at the bottom of the figure. And you have some spine switches at the top that connect all switches together. If you consider that all switches at the top are a single big virtual switch, you get something hierarchical. You can have some intermediate level switch. For InfiniBand networks, you can consider that a fat tree, and then you can do some hierarchical process placement. But there are some different networks in the wild now. So for instance, on Cray, it's very different. It's a dragonfly. So basically, you have some routers that connect different nodes. So this could be considered hierarchical. But then you have a complex topology with all-to-all connection between what's called a group of routers. And then you have some higher level groups that connect all these intermediate groups. It's a little bit hierarchical, but you have lots of links between different parts of the group. It's not exactly that. So it could work, but it's not perfect. And if you look at the number one on the top 500 right now, so the Fugaku supercomputer in Japan, it's not hierarchical. Basically, it's a torus where each node in the torus, it's something that looks like an hypercube, but it's not totally clear to me. So you can consider it's a hierarchy of a torus containing hypercube containing nodes, but all the torus information, it might be useful to know that, for instance, two nodes are connected directly on the torus, and you don't have to go across an entire ring, etc. So if you want to model that network very well, the hierarchy won't be very precise. So we tried to model the network in the past. We worked on a project called Netlog, but it's pretty much stale now. My feeling now is that we did a different model. We're not going to do something hierarchical because it's not precise enough for the network. Also, the impact on locality on the network is still important, so you really want to make sure that your model works well. So basically, my feeling now is that we don't want to build a generic model that works for all supercomputers. We will rather have something that is specific to, for instance, Torus, something specific to Dragonfly, something specific to IB. The reason is that if we build a generic model with basically a random graph that you map on top of your torus, when you perform algorithmics on top of that, if you don't remember that it's a torus, your algorithmics won't be as efficient. If you remember that it's a torus or a dragonfly, you can optimize a lot of things. So building a generic model with a custom graph is not a good idea from my point of view. Also, there are some features that are not similar across different technology, like routing. So if you try to build a generic model, you will have issues trying to make your model actually work on all these technologies. So instead of a generic model, my feeling is that we should define some generic API for answering a question, like I have two nodes, give me the distance between two nodes. And once you get this question from this query from the runtime, you look at what kind of technology you have. If it's a torus, you know how to compute the distance. It's very easy inside a torus. You might want to find some paths between two nodes or find which node are your neighbors. It's the common list of things that we have when we do some process placement on top of network. So no generic model, just a generic API, and then custom implementation for each technology. The problem is that this is a lot of work. You need access to different supercomputers, different technology, and of course, a lot of testing, etc. So this isn't easy. So we're done with the modeling. Now we're going to look at what programming models and standards do. So in MPI, there wasn't a lot of things in the past. Things are improving. So some people started working on what we call rank reordering with a function called thisGraphCreate. So the idea is that you're not going to move processes, but you're going to look at where they are running, what affinity do you have between different tasks, and you're basically going to change their role, saying you rank 0, you're going to be rank 4 because you are close to rank 5, and you have to communicate a lot with rank 5. So basically, you're going to move virtually the different ranks without actually moving the processes, because changing the binding at runtime is complicated, especially if you're not running on the same nodes. In MPI 4, which is going to be released in the next month, there will be something called MPI ComType hardware subdomain. The idea is that you have multiple MPI ranks running on the same machine, and you want to know, for instance, what are the ranks that are actually sharing a cache with me. You will be able to do that so that you can optimize some communication between them or allocate some shared memory or things like that. So this is coming soon. This is already in the standards that isn't released yet. Ideally, it would be good if the MPI forum could standardize MPI run, MPI exec options for placement. We're talking about that, but it's not ready yet. In OpenMP, there are lots of environment variables for changing the binding, like low-level things or higher-level things with OpenMP places, which work well. The problem is that when you start to combine all this, so if you have here 2 machines, you can have, for instance, on each NUMA node, 1 MPI process plus OpenMP, which means you're going to place your MPI process, okay? But inside each MPI process, you will have to run OpenMP with different configuration between each OpenMP instance. You're going to use a different set of 4 cores. This isn't impossible, but you have to be careful when doing that. Other example of what people do these days is that sometimes they don't do MPI plus OpenMP. They could do MPI between nodes, and then inside each node, they run a single process with a task graph runtime like a parsec or StarPU or something like that. And this runtime could use some parallel task like BLAS. So it means that you have to be careful of which core you give to the runtime and to the parallel task. And this is actually a big problem these days. Basically, we have different layers. So you could have an application doing MPI plus a runtime like StarPU or whatever. This runtime could use some parallel task like MKL. So you have three layers of software that will manipulate different bindings. MPI will use large bindings like multiple set of cores inside the node. Not OpenMP. The runtime will use something smaller, and then the parallel bus will use something smaller. So you have to be careful first that all these layers, they will not discover and store the topology information again, because it will take some time and will waste some memory. So they have to share the topology information. We've been working on that in the past. For MPI, it's pretty much solved now. For OpenMP, there's still some work. OpenMP is going to discover the topology again, even if MPI has everything. And also, all these layers, they should inform each other or what they use. If OpenMP is going to use 2 cores, MPI should not use the same cores, or another instance of OpenMP on the side should not use the same cores. And right now, it's difficult to do because there's basically no cooperation between all these layers. So then we need a way to make sure that each layer is going to use the core it was actually allocated, and that's not easy because basically you have to lie to some software by saying instead of giving the entire machine, I give you only these cores, and it's not easy. So basically, we need some cooperation between all these layers. There's a need for spatial cooperation, which is what I just said. You don't want different layers to use the same resource at the same time. So I say layers like MPI, OpenMP. It could also be 2 instances of OpenMP or 2 parallel BLAS or whatever. They don't want to use the same core at the same time. And also, we have some dynamic application these days. So sometimes the resources that you need is going to change during the process, during the execution. So sometimes our application would like to release some cores because they don't need them right now. And some other layers or processes or job might want to benefit from these free resources temporarily. And this is not easy because you need to manage the resources, but the grain is much finer than what you do in Slurm, for instance. You allocate 10 nodes with 10 cores, and you give them for the entire process execution, job execution. Right now, it's something dynamic with fine grain, and there's a lot of things to do. So basically, we need something to coordinate this dynamic application to understand when they need resources and what they need, and to give them what's available. And this coordinator, it needs to discuss with all these layers. So we need some kind of transport protocol. For the transport protocol, that's something that that could work. It's called PMIX. So you might know it. It's already used by basically MPI and the resource manager like Slurm. So all MPI internally use MPI-MIX. PMIX is basically used to ask Slurm how many cores did you allocate on which node. And once MPI gets the information, it can actually launch the job there. So it means the resource manager and MPI had information about the available resources. So they could give it to OpenMP2 and then could give it to runtimes. So PMIX, it's a generic thing that is basically some key value storage. You interrogate the server to get information about lots of things, and you could interrogate it to get some information about the binding of the different runtime layers. So there's still a lot of things to do here, but at least if the runtime developer want to make all this collaboration between layers work better, PMIX is a good way to start because it already has some information about what MPI is using, what was allocated by the resource manager like Slurm. So to finish, I'm going to talk briefly about heterogeneous resources. So first, there are some issues with heterogeneous CPU. So you might have heard of ARM big.little. So it's basically two processors inside the same package. Some cores are faster than others. If you want to save energy, you're going to use the small cores. If you want to have better performance for gaming, for instance, you're going to use the big cores, and the energy consumed won't be the same. Intel is going to do something similar. So people are starting to tell us how are you going to expose that in HWlog, because we want to know which core are big cores, fast cores, and which cores are small cores. That's not easy actually, because you need to define clearly the difference between cores. It could be a list of CPU features, like this core can do AVX 512, for instance, and this core cannot. So applications that want to do some multimedia things with lots of SIMD instruction will rather go on the big core. But right now, it looks like the difference between cores is basically only the power of frequency. I mean, the computing power, the frequency, some ugly details like out of order. So it's very difficult for us to define the difference between cores and to expose to application. We could say this is a big one, this is a small one, but it doesn't mean much to the application. So we're still thinking about how to expose that, and we're actually waiting for these things to come to HPC, because right now it's specific to smartphones and things like that. There are lots of rumors saying that it's coming to HPC because there are good reasons for having some specialized very fast core and some generic purpose cores on the side. So we're looking at that. One question that remains is who will actually be in charge of selecting the kind of cores that we're going to use? Is it the firmware, the operating system, or the application? We don't know. And now to finish, we're going to talk about heterogeneous memory. So as you know, in Knight's Landing, the Xeon Phi, we had two types of memory. One was DDR, normal memory, and the other one was MCD-RAM. It was high bandwidth memory, basically. Software was not ready at all to handle that. So basically, there was some ugly acts everywhere in the software stack, because you don't want to use the very fast memory by mistake. So you want to make sure you don't allocate there by mistake. Now, software support is improving, and actually we don't have KNL anymore, but we have some other kind of memory that is coming. It's called non-volatile memory, and this memory is what you can put inside the memory DIMMs that you use as normal memory in your machine. So basically, you can have DDR, which is a normal memory, which isn't very fast, but it's much slower than your non-volatile memory that you can use as volatile memory, so normal memory, but with very high capacity. So basically, you have some normal memory, not very high capacity and good performance, and some very high capacity non-volatile memory, and you have to decide where to put your memory. So the problem is the same as KNL, except that we cannot do the ugly acts anymore because it's not a single architecture anymore. It's going to be available in lots of processors and machines. So what's going to happen is that we're going to expose some performance information about the different memory, like this memory has 100 nanosecond latency, and this memory has 200 nanosecond. And applications are going to use that to to decide which memory they want to allocate on, which is not easy because when you are an application developer and you have to use latency information or bandwidth information to decide where to allocate, it's not always easy to use. So we need to work on abstracting application needs and hardware capabilities so that users know how to express their needs and they know what the hardware can do, and so you can match one onto the other. So to conclude, so things have improved a lot since 2008, but there's still a lot to do. So first, we need to be able to abstract application needs much better. The question is, what are you trying to optimize? Do you want to optimize for computing, synchronization, or something else? And depending on that, you're going to place your processes differently, use different level in the hierarchy, etc. We also need to better abstract the hardware capabilities. Right now, we have a structural modeling of the hardware, which doesn't give any quantitative information like latency bandwidth, but we are actually going to change that because at least for memory, it's important to give quantitative information because that's the only way people are going to choose between two kinds of memory. And once you have this better abstraction for software and hardware, productivity will be better because your process placement should be automatic now. You just have to basically abstract your new machine, you port your application there, and the placement will get updated automatically. And what's important to me is that we need coordination between software layers because right now it's a big mess. We have lots of runtimes and they basically don't talk together. Or if you try to do that, you have to use lots of environment variable and complex things that don't work very well. So we cannot keep doing that forever. And I'm Doc for this. I want to thank a lot of colleagues. I could not list everybody, but we've been working on that with lots of people. So thanks to all of us, and thanks to you for listening. I can't hear you very well.
Merci beaucoup. I think this is one of the very few expressions I can know in French. So that was very enlightening. It was a very nice talk, and especially because you know, it reminds me of lots of things that I did in the past. So it's quite nice. We have here lots of questions, but we have just 3 minutes.
Sorry.
It's okay. I mean, you talk. I mean, that was wonderful to me. So let's go for questions. The first one is, I'll try to be quick. The first one is by Lucia Drummond. When we run a multi-threaded MPI application in a cloud environment, how to know the memory hierarchy to take the best scheduling decisions?
So for virtual environment, as far as I know, the virtual hierarchy should somehow reflect the underlying physical hierarchy. At least we've been working with some virtual solution developers, so that's what you see. So if they are exposing the correct information in the virtual machine, it should just work, hopefully. If they don't, you just allocate memory, you don't know where it's going physically, so performance won't be very good. So basically, it's a matter of if the virtual machine is doing the good work to expose the underlying hardware.
Okay, I think this answers Lucy's second question as well, because you talked about the virtual machine. So Lucy has another question that is concerning the memory CPU, GPU. Can a GPU be closer of a new node than another one? How to discover it?
So right now, I don't think it's the case, but it's coming. I think in the new CPI specifications, there's something like that, where some memory can have its best, what we call initiator, be a GPU or an accelerator instead of a CPU. We're looking at that. It's not totally clear to me how we're going to expose that. Right now, the edge block model doesn't really like having some memory that is not close to CPU, but rather close to GPU. Tweak that. So I'm still waiting to see a machine for that, but it's going to happen in the near next year. So we should talk about that again in a couple of years.
So another question by Philippe Navo. Can you say something about GPU and FPGA placements?
So my understanding is that when you submit a kernel on GPU, you don't know what's going to happen. You just submit it. You have no way to choose, is it going to use that part of the GPU or this other part? So basically, you don't really do any scheduling or binding in there. On the cores, you can select which task is going to run where. On GPU, you just launch the kernel and you hope it's going to run very fast, and that's it. So as long as we don't have any control on that, we cannot do anything. Actually, it will be good if CUDA could say, I don't know, you submit 3 kernel, I'm going to run this one first and then these 2 guys at the same time. Maybe it will be useful for people that are actually optimizing the scheduling of their task. But right now, I don't think there's any way to do that. So maybe in the future, because, oh, sorry, wait.
Sorry, how about the FPGA?
I assume it's the same, but I'm not sure. I don't know FPGA very well. So I don't know if an FPGA can run 2 things at the same time, for instance. So I don't know, sorry.
Well, yeah, Philippe, I don't know if you want to say something about your question. We are running out of time anyway.
No, it's okay. It's okay. It's just to have an
I
idea.
I have just one final question. That is, I mean, I work with parallel systems and fine tuning and brushing bits, blah, 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 in the past. So is this a recurrent problem? I mean, whenever you have a new hardware and you need to change your application from hardware to another, you need to do, again, the same thing.
Yeah, that's what we really want to stop, because it's really, well, my hope, I don't know, 5 or 6 years ago was that the hierarchy was not changing anymore because they will not add some new levels, etc. But I was wrong, and it's changing again right now. So yeah, so people will have to adapt again, and I don't want this to keep changing. So we really need to work on abstraction because of that. Once the application really knows what it wants, it shouldn't be a problem anymore. But right now, we still have lots of work to do to actually solve that.
All right, thank you very much, Brice. We are running out of time, so I want to thank you very much again for this excellent talk. I hope everyone enjoyed it. And I'm going to give the word to Alfredo. That's going to be the chair of the next session. Alfredo, are you there?
Thank you.
You're welcome. Alfredo? Devia ser o Agosto? Não, é o Alfredo Goldman. É o Agosto. Devia ser o Agosto. Pois não é, depois é só. Alfredo, are you there? Does anyone know about Alfredo? He was supposed to...
Inês, I'm trying to call him, but he's not answering. I'm calling him, okay? I don't know what happened. I'm calling him now, but he's not answering. I'll keep trying, but I think it's better to start the...
Yeah, I think as well. So,
okay.
We'll start our next session then. Session 5, and our first presentation is going to be exploiting non-conventional DVFS on GPUs, application to deep learning. Are the authors present?
Yes, I am. Good morning.
Good morning. We are going to play your video, and then we have time for questions, okay? Thank you.
Perfect. Hello, my name is Francisco Mendes and I'm with Inês Guidé from Lisbon, Portugal, and I'm going to present my paper entitled Exploring Non-Conventional DVFS on GPUs, Application to Deep Learning. In the last few years, deep neural networks are having a significant impact in industry and society by allowing for important breakthroughs in many application domains. However, DNNs are usually characterized by significant computation burdens, particularly when considering the training of very deep and complex networks. GPUs are the primary computational devices used to train these complex networks, being able to achieve the greatest amount of performance while being easy to use. When trying to maximize the energy efficiency of GPUs, many approaches can be followed, like the use of low-precision arithmetics or the more widely used dynamic voltage and frequency scaling. DVFS carefully selects the voltage-frequency pair in accordance with the GPU use. AMD and NVIDIA present the concept of performance levels in their DVFS systems. These are the predefined voltage-frequency pairs that their DVFS system chooses according with the GPU use. As can be observed, the lowest performance levels achieve a lower performance and power consumption by using a lower frequency and voltage, while the highest performance levels use higher frequency and voltage to achieve higher performance. The convention of VF configuration increases the voltage linearly with the frequency to guarantee a safe voltage margin and correct GPU operations. However, by exploring this voltage margin, it is possible to achieve the same performance levels with reduced power and energy consumption, being this the main idea behind our work. And so we evaluated the degree of undervoltage that is couped by each frequency, analyzed the benefits and drawbacks of working with those non-conventional VF pairs, and finally, we applied this exploration of non-conventional voltage frequency to the training and inference of convolutional neural networks. The main contribution of our work is the development of a methodology to evaluate the use of non-conventional voltage frequency on GPUs. This methodology can only be applied to AMD GPUs due to being the only manufacturer that allows for independent control of frequency and voltage. On the rest of the presentation, I'm going to demonstrate the developed methodology, followed by the application of it on an AMD Radeon Vega 10 Frontier Edition, showcasing the usable voltage margin, the limiting architectural components to it, and the benefits of working with such configurations. Finally, I'll present the results of applying this knowledge on the two more energy-consuming CNN layers, fully connected and convolution, concluding by presenting the behavior of CNNs when trained with those non-conventional voltage-frequency pairs. The developed methodology acts on characterizing the effects of undervoltage across the usable frequency spectrum for each of the GPU architectural components. The GPU has two DVFS domains, core and DRAM, and, depending on the component under test, the corresponding domain is explored. The objective of the methodology is to create a usable exploration space that can be used for the target GPU and to understand the energy performance behavior across the exploration space. In more detail, the target benchmarks characterize the DRAM, cache, and shared memories to assess the minimum read and write voltage and the occurrence of data corruption, the LU with the multiply and accumulate and special function unit to check for computation errors due to timing violations, and the two final benchmarks assess the correct kernel execution for heavy branch kernel and mixed workload, testing the GPU thread scheduler. Starting with the DRAM domain, independently of the voltage being used, no errors or data corruption has occurred. This component can work with any of the available voltages. The linear increase of the voltage with frequency only exists for a better match between DVFS domain's voltage. For this benchmark, the parameter OP controls the number of DRAM requests over time. As expected, for memory-bounded kernels, scaling up the frequency results in better performance. The improvement in the computation time also translates to energy consumption reductions. For compute-bounded kernels, DRAM frequency scaling does not significantly impact performance or energy, prompting us to conclude that it is always better to set the DRAM frequency at the highest performance level, since scaling down the DRAM DVFS only affects the energy efficiency negatively. For the cache benchmark, the parameter OPS controls the number of cache requests over time, and so it impacts the stress over these components. It was found that decreasing the cache pressure allows for a greater amount of undervoltage, and that no data corruption occurs at lower voltages. Since the cache did not prompt any data errors but is still being affected by the number of data requests, we conclude that the state machine responsible for controlling the data movement is the component that is limiting the undervoltage capabilities. In general, the cache limits the voltage exploration space for memory-bounded kernels. Next, we emphasize the multiply and accumulate operation. The developer benchmark tests the effects of non-conventional VF scaling and the effects of dependencies on the code. The results attest that a kernel that has a significant number of read-after-write dependencies between operations is not able to be undervolted as much as a dependency-free kernel. The energy performance chart displays an interesting phenomenon, where performing undervoltage at the highest frequency allows not only for an energy reduction but also for a performance increase. After careful examination, we explain this phenomenon by an overall reduction of the power consumption, allowing the GPU to always be under the power cap when undervolted. The presented chart compares the voltage margin across all benchmarks. The results reveal that a regular GPU has between 150 to 200 mV of safe margin of undervoltage. In general, it was found that the DRAM DVFS does not determine the size of the voltage margin and that the cache LU limits the undervoltage for memory-bounded kernels and the LU limits for compute-bounded kernels. The fully connected layer is a wraparound matrix multiplication, which in turn makes use of the MAC operation. Hence, the CNN layer energy performance behavior is similar to the results of the LU MAC. Depending on the layer's input size, the fully connected layer undervoltage limits are bounded by the cache L2 for large inputs or the LU for small inputs. The use of non-conventional VF pairs allows for an EDP improvement of over 50%. Computing the convolution on the GPU can be performed with three different algorithms: direct, using the traditional mathematical operation, NGEM and Winograd, based on matrix multiplication. For all algorithms, both the training and inference benefit from being executed under non-conventional VF, with these configurations being able to achieve better performance and energy consumption than the conventional VF scaling. In general, the exploration prompted an EDP improvement of 40% over the highest performance level. As stated, using such non-conventional VF scaling can result in the occurrence of computational errors, mainly induced by timing violations on the LU. To understand the degree of computational errors and if those can neglect the use of non-conventional VF pairs, an analysis of the layer's output was done. When using the maximum undervoltage, 98% of the results are still correct for the fully connected layer, and, looking at the distribution of the relative errors, even in the worst case, the error is smaller than 0.14%, with most of the errors being inferior to 6 to the power of -6%. The results of the convolution layer are in the same magnitude. In all algorithms, besides inference with GEM, it was observed that between 96 and 99% of the outputs are correct, with the relative errors of the wrong outputs being always smaller than 0.08%. The presented table displays the final training accuracy of 4 CNN models, AlexNet, LeNet, VGG11 and WideResNet, under different amounts of undervoltage. As expected, performing the undervoltage with its increasing rate of computational errors did not significantly impact the final network accuracy. Hence, we conclude that the nature of the NAND training procedure can cope with small percentage of computation errors and still achieve a correct output. The possible computation errors that occur and their effects are not propagated to subsequent training epochs. The resulting weights of the training procedure are valid regardless of the amount of undervoltage being made. Knowing that it's safe to train the models in such circumstances, the presented charts compare the default VFS systems of the GPU while training the networks with two of our non-conventional VF configurations. These are the lowest voltage possible while using the highest GPU frequency and the VF configuration that achieves the lowest EDP. As shown, using the configuration that achieves the best EDP improves this value by more than 50%. This improvement comes from the reduction in energy consumption and has the added benefit of not impacting the total training time. So, the proposed VF configurations can improve the GPU's energy efficiency when training DNNs without any noticeable drawbacks for the final user. The results of our work builds a groundwork that indicates that non-conventional VF allows for the utilization of higher frequencies with the energy consumption of the lowest ones, allowing to improve energy efficiency without penalizing performance, and that this configuration should be utilized on the training of DNNs with great benefits. These conclusions come from the ability of regular GPUs to be safely undervoltage and having a VF exploration space tightly defined by the cache and LU voltage limits. Overall, the use of non-conventional VF scaling reduces the ADP of the fully connected and convolution layer by more than 50%. And these results directly translate to an EDP improvement over the complete training of CNNs of up to 37.6%. Thank you so much for watching, and I hope to talk to you on my session on September the 10th. Goodbye. Hello,
Hello, Francisco. Thank you for your presentation. Let's see if you don't have still here many questions, but I would like to ask you, in terms of application dependency, can you how is dependent the application that you are using for the results that you get in terms of performance?
Well, first of all, I'm not able to start my video, but
I can't hear. I could not hear the question.
Okay.
No, I was asking if the performance that you obtain is dependent of the application, or
yes, so if you look we conclude that the two main components that limit the exploration space and the VF pairs that we can use are the cache and the ALU. And depending of the application is more compute bounded or memory bounded, the improvements that we can achieve will look more as the result of the benchmark of the cache looked or the ALU looked. In general, we saw that more compute-bounded application yields a better performance when using our non-conventional VF pairs.
Yeah, okay. So, but if I have a new application, what I have to do to get advantage of your methodology? I have to profile what is needed.
Well, if you already had profiled your GPU, your specific GPU with our methodology, where you run all kinds the 8 benchmarks that we develop and create the exploration space, then you just need to run your application while testing all the possible VF pairs that are allowed for your GPU. You don't need to do something specific to it, because since you already characterize the GPU as a whole with the specific needs, you just need to try to see which configuration achieves the better output for you.
Okay, Francisco, I think there is no other questions for now. I will finish here. Thank you very much.
Thank you so much.
Okay, bye. I think Alfredo is already online. I will pass to you.
Okay, thank you very much. Sorry, I just have a technical problem on the time. So let's go to the second presentation. Sorry, Francisco, thank you for your presentation. Now it's by Nicholas Baum Agostini and for Northwestern University. Please, video.
Hello. Hello, everyone. Hello, my name is Nicholas Baum Agostini, and I am a PhD student at Northeastern University. Today, I would like to introduce you to our paper called Designing Space Exploration of Accelerators and End-to-End DNN Evaluation with TF-Lite SOC. This presentation will cover the following topics. First, I will speak about the motivation for this work. Then, I will explain our framework, TF-Lite SOC. And finally, I will talk about the case studies that are enabled by our framework. In recent years, we have observed an explosion on the number of applications that can be enhanced by machine learning algorithms. These applications fall under several different fields such as computer vision, natural language processing, the medical field, graph analytics, games, information reasoning, and others. These two images were extracted from the Papers with Code website. On the left, I show you a small subset of these applications. On the right, I show you a graph with different deep neural network models targeting better image classification. The y-axis of this graph presents the number of parameters present in each of these models. As you can see, the number of parameters has been increasing with time. Compare with the champion of the 2012 ImageNet competition, AlexNet, which had around 60 million parameters. Papers that currently hold the top score on ImageNet challenge have north of 500 million parameters. The number of parameters has a direct correlation with the number of computations that need to be performed to execute these models. In order to accommodate the increased computation demands, the research community and hardware manufacturers have developed accelerators to execute those models faster. This table shows a small subset of the accelerators that have been proposed in the recent years. But now, a different question arises. How do you compare these different accelerators or new hardware features that may have been modeled using different technologies or different benchmarks? Some of these accelerators have not been integrated with standard ML frameworks, and the only comparison that would make sense would be raw throughput or power numbers. But if you look at the year and the gigaops per second columns in this table, it is not always the case that the gigaops are increasing over time. Why is that? Aren't we making forward progress in this field? In this work, we claim that the fair metric of comparison is end-to-end DNN execution runtime. With this metric, it would be possible to compare different architectures or optimizations fairly. Recent work on simulators of DNN accelerators have proposed end-to-end DNN runtime estimation. However, there are some caveats. SMAP, proposed in 2019, offers end-to-end DNN acceleration simulation. However, it is not integrated with a standard ML framework. Storm, published in 2020, is integrated with the Café deep learning framework. However, it does not use a system modeling language. Instead, it implements its own modeling mechanism, but this approach, adopted by Stone and other simulators in this list, prevents a straightforward path for accelerator synthesis in the future. Targeting these missing features, our work introduces a framework for end-to-end evaluation of DNN accelerators during inference within TensorFlow Lite, an industry-standard framework for machine learning. Our framework provides a set of configurable modules currently implementing a TPU-like accelerator. These modules use SystemC system modeling library for C++. SystemC is another industry standard which can be used by high-level synthesis tools in the future. With our framework, we present the performance and bottlenecks of a baseline accelerator. Then, we analyze the patterns and propose applying compression to derun accelerator memory traffic. Finally, we discuss the results of our studies and we show that our compression technique can provide up to 1.19x speedup during end-to-end DNN execution. The FlightSoc simulator framework is an open source project available at this GitHub link. In the next slides, I will elaborate on some of the key aspects of the FlightSoc listed here. The FlightSoc integration with TensorFlow Lite allows for the execution of any TensorFlow Lite DNN model. Simulated accelerator runtime will be captured as long as a TF-Lite operation of interest is executed. Currently, we focus on the acceleration of convolution operations that are implemented with general matrix-matrix multiplication kernels. During DNN execution, a TensorFlow convolution will call the gem, and a SystemC simulation of the TF-Lite-SOC accelerator will start. The modules in the dashed box are implemented in C++ with SystemC. Stimulus is in charge of intercepting the gem operation input data and matrix dimensions, and scheduling the operation in the accelerator. Currently, there is no runtime driver for the accelerator, and the stimulus block is in charge of handling the operation, such as calculating an optimal tiling to best use the accelerator resources. Once the operation is completed, the TF-Lite-SOC lets TensorFlow Lite continue the DNN execution until the next operation of interest is called. Here, the monitor block collects metrics about the individual execution to be later summarized with the end-to-end execution metrics. The accelerator, also called device under test or DUT, will be further explained in the next slides. The accelerator modules were developed with the SystemC incremental design refinement approach, and this is the recommended way to design new modules or a brand new accelerator for TF Flight SOC. First, an algorithmic model that ensures correctness is implemented. Then, a specification refinement step is performed, mapping or translating this algorithmic model to a functional unit. This step produces an untimed functional model. Then, time annotation is performed for new functional units, generating a timed functional model. Finally, channels and interfaces are mapped in the communication refinement, producing a bus cycle accurate model. In the future, processor and synthesis refinement will be enabled for current modules, allowing for accelerator synthesis. The incremental design and refinement approach allows module implementation descriptions to be refined only until it captures the desired functionality. If, for example, a new tiling strategy optimization is implemented, we can just swap the accelerator control module with a new algorithmic or untimed functional model, and only refine further if the functionality and behavior of the full accelerator meet our expectations in terms of performance and correctness. Currently, the baseline accelerator implements a systolic array architecture displayed in this figure. This architecture is inspired by, but not the same as a Google TPU. During kernel execution, the stimulus will communicate with the control module that will orchestrate the accelerator operation. After receiving the information from the stimulus module, the control module will, for example, tell when, what data, and how many elements the DMA engine should bring from the DRun module into the accelerator feature map buffers. The control module will also tell when the systolic array should start processing the data from the input buffers. We expect that future systolic array optimizations could be built on top of this baseline, but we also hope to reuse some of these available modules to implement new accelerators. The case studies discussed next utilize the embedded topology displayed on the left figure and the mobile and low power configurations shown in the table. For detailed explanation on these or additional system configurations, please take a look at our paper. Now, we are going to talk about our case studies, starting by the scaling up and PE utilization study. In our paper, you will find these graphs which show the normalized latency breakdown per type of operation of the end-to-end execution as a bar graph. Each group of 3 bars represents a different type of benchmark. In this case, M1 represents MobileNet V1 workload with FP32 data type using the low power configuration. The 3 bars show how the system is scaled up or down, considering the number of PEs reduces by a factor of 4 as you look at the next bar to the right. The latency numbers are normalized to the baseline 256 by 256 PE array, the first bar, but the total latency is annotated on top of each bar. The red circles in the bars show the PE utilization in percentage. Here, we see that as we reduce the number of PEs, the compute latency increases, which was expected. But more interestingly, as we reduce the number of PEs, the PE utilization dramatically increases, almost doubling from 10% to 20% as we reduce the number of PEs in this benchmark and configuration. We actually observe this behavior in all benchmarks and configurations. The 128 by 128 and 64 by 64 accelerators appear to offer much better utilization. This shows that these sizes should be considered for a scale-out study instead of a monolithic 256 by 256 accelerator. Another interesting factor, which is focus of our next case study, can be observed. Some benchmarks with the mobile and low power configuration show long latencies associated with DRun, read, or write. In the next case study, we will propose a compression mechanism to reduce this DRun, read, and write latency shown in the purple segments. This solution is a more feasible approach than just increasing the transfer bandwidth, which would require working with a different interconnect technology. For compression, we have selected the frequent pattern compression technique proposed by DAS in HPCA 2008. FPC is able to compress zero words, words with repeated bytes, and narrow words in an efficient manner. We model the FPC latencies when stream DRAM accelerator memory transfers occur. For detailed information on FPC capabilities and how it compresses these patterns, please check our paper. This graph shows the size of the total data that is transferred between accelerator and DRAM module during end-to-end execution. Each group of 2 bars represent a different network model/data type combination. The presence of different patterns represented by different colors in these graphs show that techniques such as FPC is relevant, as targeting a unique pattern would not be good enough for all these benchmark combinations. Here, we observe that the FP32 models show a considerable amount of zero-word patterns, which can be reduced to 80% of the total size. The int8 models show a much higher amount of narrow word patterns, such as half-word side extended. These can be reduced to 90% of the total size. These data size reductions directly translate into a reduction on DRAM read and write latencies. Performance increase range from 3% on the int8 models to up to 1.19x speedup in the end-to-end execution of the FP32 models. This shows that this is a valid and relevant approach for these configurations and benchmarks. In summary, we introduced TF-Lite-SOC, a framework for end-to-end evaluation of DNN accelerations within TensorFlow Lite. Our framework contains a set of adjustable System C modules that currently implement a TPU-like accelerator. We have also shown you some of our scaling up studies, as well as promising results due to compressing the DRAM accelerator memory traffic. If you'd like to learn more about our work, I invite you to read our paper or reach out to me at this email. Thank you very much. Thank you.
Thank you very much, Nicholas. First, I have a question. Yes. I have a similar work as yours, but I work more on the trying to reduce the precision of the network. That means if we use less bytes, less bits on some layers, there will be no difference on the result, on the final result. And I was starting to be very curious on how I could save some energy on it. Do you have any hint on it?
So this energy is like energy work is a thing that we are planning on the future, and we are planning to enable like reporting energy within our accelerators using the Accelergy framework, on which you collect action counts with metadata, for example, the sparsity of the matrix, and you have like a table that associates energy with these actions, and then you can estimate energy. And we are planning to enable it in the future. But obviously, working with like smaller matrices, for example, int8 matrices instead of FP32 matrices, would provide you with not only runtime savings, but also energy savings, right?
Mm-hmm. Sorry?
Go ahead.
I'm also curious, you talked about free software. Do you have another users from outside your group?
Yeah, not currently, not outside of our groups, because we have this work along with University of Glasgow, University of the Barcelona Supercomputing Center, and the Universidade Santo Antônio de Murcia. So currently, those are our users. So we are hoping to get more attention and get more users in the future.
Okay. I'm not seeing any question on Slack. Maybe there is one in YouTube, but I have another question for you.
Yes.
One big problem when you have to do synthesis, real synthesis, is that it takes a lot of time. Mm-hmm. How are you planning to take with it?
So I think a good path that this system provides is that before you going down to synthesis, you would be able to model your work and like arrive into an approximation of the desired runtime that you want. And only then you go to synthesis. We actually have a group in the University of Glasgow doing exactly that. Instead of like synthesizing every single design that they have, they will first like model and simulate and only then synthesize. So this is one of the advantages of using the simulator, right? But you're right. We currently are tied to synthesis times associated with the commercial tools available, right? So, and the path that University of Glasgow is using is like high-level synthesis through the Xilinx tool in order to translate the System C modules into the actual synthesis.
And do you have any hint of how much time does it take to do a synthesis?
So yes, like from 15 minutes to a couple of hours, depending on like the size of the design that you want to do.
Okay, not so bad. I was thinking about 6 or to 10 hours. Not so bad. Okay.
So I foresee that as you increase the design and you make like the design more complex, yes, the synthesis tool will have like a harder time to synthesize. But again, I cannot speak firsthand because I have not worked much on this aspect. This streamline, this path is like one of the future work for the applied SOC.
Okay, we have a result here, a question here. I don't know if you have in your paper, someone is asking, but are the results produced by accelerators the same as the sequential in terms of quality? Can you compare the results of the sequential with the accelerators?
So,
quality?
Yeah, in the paper, I have not compared against different accelerators, but I have provided our estimation for end-to-end execution, considering the different configurations that we provide. So this is an interesting and tricky part. It's one of our motivations. Comparing different accelerators is a little bit tricky if you cannot provide this end-to-end runtime estimation, right? Because some accelerators benchmark different types of kernel, different size of kernel, and they also benchmark like with different technology nodes. So sometimes the only information that you can compare across different work is raw throughput. And we have observed that raw throughput may not be a meaningful information for comparison. But looking at our paper, you will find end-to-end DNN execution estimations, and this would be able to be compared against different accelerators and CPUs.
Oh, sorry, the question was about the DNN results, the end results.
Yeah, so in the paper we provide some end-to-end results. Like most of the figures are end-to-end inference estimations, and this can be compared. And we compare against like CPU runtimes, and we always did better than CPU runtimes.
Okay, yeah. Thank you very much. Congratulations for your work. And
thank you for the
let's
questions.
go to the next presentation. Now you have Rico from Augsburg. So please, could you turn on the video?
I'm Rico Amslinger from University of Augsburg. Welcome to my talk about hardware multi-versioning for failed operational multi-threaded applications. Current approaches to fault tolerance suffer from several disadvantages. They often rely on specialized hardware which cannot be used for any other purposes. If an error occurs, only few approaches can recover from it by themselves. If an approach supports recovery, it often comes at a high price in terms of high chip area, power consumption, or performance. Many approaches trade error detection latency for performance. This trade-off might be acceptable for large supercomputers, but embedded systems which regulate components at a high frequency require a low error detection latency. Heterogeneous multicores like ARM Big Little are often not supported, as the tight coupling used in those approaches requires the use of homogeneous cores. Finally, most approaches to fault tolerance only suffer single-threaded applications. They cannot handle the required synchronization and the simultaneous memory accesses which occur in multi-threaded applications. Therefore, there is a need for a new approach to fault tolerance aimed at modern embedded systems. This presentation is structured as follows. You've already heard the motivation. Next, an explanation of our approach follows. This includes a description of the baseline architecture, loose coupling for fault tolerance, and the challenge of execution order in multi-threaded applications. Afterwards, I will present our evaluation, consisting of a performance and error detection latency analysis. Finally, a conclusion will finish this presentation. Our approach is aimed at shared memory multicores. They must provide a hardware transactional memory, like Intel TSX, which we extend to support for.
Sorry, we have a technical problem. Just 1 minute, please.
Okay, no problem.
Só para não haver dúvidas, para não lançar o fecheiro errado. Descer a apresentação 5, certo? Ponho aqui nos 2 minutos.
They must provide a hardware transactional memory, like Intel TSX, which we extend to support fault tolerance. Transactional memory is a synchronization solution inspired by database transactions. It is implemented by extending the data caches. For our approach, it ensures the isolation to prevent faults from propagating. Hardware transactional memory also provides rollback capability. They must provide a hardware transactional memory rollback like Intel TSX, which we extend to support fault tolerance. To implement transactional memory is a synchronization solution inspired by database transactions. The memory is implemented by extending the data cache. For our approach, it ensures the isolation to prevent faults from propagating. Hardware transactional memory also provides rollback to provide a hardware transactional memory rollback like TSX, which we extend to support fault tolerance, which are run redundantly on a leading and a trailing core. In our implementation, these sections are encapsulated in transactions to make use of pre-existing isolation and rollback capabilities. Each transaction is first executed by the leading core and then by the trailing core. The leading core can already continue execution speculatively, as long as it has sufficient resources available. Note that the approach can handle different execution times on the leading and the trailing cores. Such differences can occur because of variable memory access latencies. However, heterogeneous cores executing the same instruction set are also supported. While the transactions are running, the cores calculate a checksum consisting of all memory and register writes. These checksums are compared once both cores have completed their transactions. If they match, speculative resources can be freed and execution resumes normally. However, if there was a bit flip, the checksums will not match. In this case, global rollback is initiated. All cores need to roll back to the latest confirmed state. This can be realized by aborting the pending transactions. The cores then restart at the beginning of the offending transaction. If the fault was transient, it will not occur again and the checksums now match. When When extending this approach to multi-threaded applications, there is the challenge of execution order. Assume a system using classic transactional memory. This flowchart shows the executed transactions, their instructions, and the state of memory. The application runs two transactions accessing the same variable called data. Therefore, transactional memory will ensure that they are executed sequentially. These transactions are executed redundantly on the leading and the trailing cores. On the leading cores, thread 1, which increments the variable by 1, is executed first. Afterwards, thread 2 XORs it by 1, resulting in the final value of 0. However, on the trailing cores, the execution order is reversed. Thread 2 XORs first and then thread 1 increments. Therefore, the final result is 2, which does not equal to the 0 calculated in the leading execution. The mismatch is detected and global rollback is initiated. We have solved this issue using multi-versioning. In a multi-versioning system, there are multiple versions of each memory word. The transaction in which code is executed determines which version to read and write. When thread 1 commits its transaction on the leading core, its result is stored in v1. Thread 2 reads v1 and stores the result in v2. Therefore, the trailing transaction of thread 2 will also read v1, even though the trailing transaction of thread 1 was not run yet. Consequently, all trailing transactions read the same values as their corresponding leading transactions, and their calculations return the same results. This allows our approach to run multi-threaded applications on loosely coupled cores without any unnecessary rollbacks. To evaluate our approach, we have implemented it on a FPGA. We have also ported the pthread library to transactional memory, which we then use to run the PASIC benchmark suite. In total, we have evaluated 10 of the 13 PASIC benchmarks. Trackmine does not support pthread, so it was left out. Fluid Animate and FaceSim could run but do not support arbitrary thread counts, which makes them unsuitable for our evaluation. We have evaluated performance and error detection latency. This figure shows the speedup of the benchmark VIPs running on 1 to 12 cores. All numbers are relative to the execution on one core without redundancy. We also use the execution without redundancy as our baseline. We then ran the benchmarks with redundancy enabled. Note that these runs are true multi-threaded runs. As expected, the execution with redundancy is lower than the execution without redundancy. To determine whether the performance is good, we calculated a range, which we expect the performance to fall into. The upper bound of the range is determined by running the benchmark twice in parallel with half the cores for each instance. This is always faster than our approach, as it does not perform any comparisons. The lower bound of the range is given by running the benchmark twice consecutively. This is lower than our approach, as the benchmark does not scale perfectly. As you can see, our implementation is in the expected range. Charts for the other benchmarks are available in our paper. Of the 10 benchmarks we used, 7 performed well without modifications. There are two main issues: false sharing and race conditions. False sharing occurs when two threads access different words in the same cache line. This results in a transaction abort and bad performance. Race conditions also cause transaction aborts and bad performance. Note that it is not our approach which causes these race conditions, but only makes them more obvious, as now the application also runs slowly. Race conditions should really be fixed before shipping an embedded system. There is no use in a fault-tolerant system if the likelihood of your application crashing because of a race condition is higher than the likelihood of a single event upset occurring. When running the benchmarks, we also noticed that simple fixes can improve performance greatly. For example, one benchmark used an incorrect cache line size. Correcting this massively reduced false sharing and improved performance. We have also evaluated the error detection latency of our approach. In most cases, the actual transaction size is close to the target of 10,000 cycles, and a trailing core is immediately ready to confirm the transaction. Therefore, on average, most errors are detected after about 10,000 cycles. This should be sufficient for most embedded systems. For comparison, the duration of a single benchmark run is in the magnitude of billions of cycles. However, due to the speculative nature of transactional memory, there are spikes in latency. These are mostly caused by different cache states in the trailing core, which causes the trailing transaction to take more time than the corresponding leading transaction. Our FPGA implementation also suffers from the limitation that transactions can only commit, add a memory operation, as modifications to the closed source cores would have been necessary to allow arbitrary commits. A real implementation should not suffer from this limitation. To summarize, let's recall the disadvantages current approaches suffer from. Our approach, on the other hand, has resolved these disadvantages. While classic approaches to fault tolerance rely on specialized hardware, our approach uses a general-purpose transactional memory, which can also be used for synchronization. Other approaches have an additional cost if recovery is needed. However, our approach uses the recoverability included in the transactional memory. It also features a low error detection latency. Contrary to most previous approaches, heterogeneous multicores that execute the same instruction set are supported. The execution of shared memory multi-threaded applications is also possible on our approach. This concludes my presentation. Thanks for watching. Please like and cite.
Sorry for the technical problems.
Oh, the second one today. Thanks, Rico. Are you there, Rico? Okay,
yes,
I'm seeing you. Thank you for your nice presentation. And I have a couple of questions here that I would like to answer to me. I see your technique as very good because it can do the recover of the fault, while usually the fault tolerance usual ways on the hardware, they just notice that there's a problem. So my question is, could you combine both to be more efficient, kind of hardware checking some, for instance, and your technique when there's a problem just to roll back to be more efficient?
You could think about that, but you have to find a fault detection mechanism which is more efficient and still detects all errors reliably. Because our approach also has the advantage that it can be used on heterogeneous multicores, and then you only have a small core which checks the leading core. The trailing core is just basically on armbit little, you would use a little core for the trailing core. And then it is really efficient to detect the errors that way.
Okay. We have a question from the audience. Does the presented results depend on the failure model used? Injected failures, for instance?
The presented performance numbers and error detection latencies are without any injected faults. If you inject faults, then the performance will, of course, be slower because the recovery does take some time. You have to repeat the transaction which contained the error and also all other transactions on the other cores. So if you have common faults, it will get slower. And another thing to note is that we only monitor the pipeline. So if you assume a fault model where other errors are injected into the memory, for example, you need additional mechanisms for this too, which might cost additional performance.
Okay. And if you have a program that a system that you know that there will be more failures on some parts of it, can you adapt your mechanism to have kind of speculative fault tolerance to focus more on certain parts?
You can increase the number of trailing transactions which validate a single leading transaction. So basically you can switch to a kind of a triple modular mode, but you have to make additional extensions so that you get additional performance from it, because it would just make the error detection more reliable to have more trailing cores. But in case of an error, they wouldn't vote or something like that. You still would need to roll back and it would cost performance. What you can do is you can modify the scheduling. So if you know one core is very susceptible to faults, you would use that core as a trailing core, which has the lowest priority. so it is only used very rarely. And that would perhaps avoid some faults because the core is in idle while it occurs.
Maybe, yeah. Then that can be an idea from future work, maybe. Okay, so thank you very much for your nice presentation. And now let's go to the last paper of the section from Said Ali Hassan from Texas A&M. Could you please put the video?
Hello, I am Said Ali Hassan from Texas A&M University, and I welcome you all to this presentation on our paper, On-Chip Parallel Photonic Reservoir Computing using Multiple Delay Lines. I will begin by discussing what reservoir computing is, and will discuss a popular model used in its hardware implementation. I will then discuss the motivation behind our work before discussing the proposed architecture, its evaluation, results, and analysis on them. Reservoir computing is a subset of recurrent neural networks. It is an emerging paradigm in classification problems as well as time series prediction problems. Reservoir computing comprises of input layer, reservoir layer, and an output layer. The figure here shows what the model looks like. It has a feature extractor part and a feature classifier part. The feature extractor is comprised of input layer and the reservoir layer, whereas the output layer is the feature classifier part. What's different from recurrent neural networks is that in this model, reservoir layer is untrained. The weights and the connections are random. The principle behind reservoir computing is that the input layer distributes data to reservoir layer through some fixed weights. Neurons in reservoir layer are all randomly interconnected, and their transient states at any point is given by equation 1. The transient states are fed to output layer through some weights Wi. This particular weight matrix Wi is trained on the features extracted from the feature extractor part. All other weights in this model are random. Due to having many neurons which have nonlinear characteristics, the hardware implementation of reservoir layer has been very challenging. Researchers have come up with a delayed feedback reservoir model which uses a nonlinear node along with some delay loop and temporal encoding scheme to perform all the computations of the reservoir layer using these three elements. This has given rise to a single node photonic computing model, which is shown below in the figure. The coupler here receives discrete masked input from the input layer and a feedback signal from an optical to electrical converter. Each sample of the input acts as a state of the neuron. The nonlinear node receives the sum of masked input and a feedback state of the neuron and transforms it into a new state. All these states are collected and fed to an offline computer which trains the output layer. Using the single-node photonic computing model that we just discussed, multiple photonic implementations of reservoir computing have shown very promising results. These implementations have used a single layer of reservoir computing or multiple layers of reservoirs to perform reservoir computing. However, all of these implementations use a fiber spool, which is an off-chip component. For example, in the figure below, we see a fiber spool that was used by one of the researchers and is 1.7 kilometers in length. Obviously, this is not desirable. Also, current architectures do not exploit the inbuilt parallelism of reservoirs. The reservoir that is being used is independent of the task being performed, and multiple tasks can use this reservoir, even at the same time. Also, state-of-the-art available components can enable us to design new on-chip architectures, since device physics have improved multiple folds. This motivates us to design a new architecture that is not only on-chip, but can also perform jobs in parallel. Before discussing the proposed architecture, we first discussed two of the components that are crucial to our design. Mach-Zehnder modulator is used as a non-linear element. The figure below shows a schematic of Mach-Zehnder modulator, or MZI. It is basically two waveguides in parallel connected at both ends by a Y junction. Laser light comes into the MZI at one end and can be collected at output end. By applying electrical data, we slow the propagation of light in one of the waveguides. This results in a modulation which we can collect at the output. The second component that we use is a micro-ring resonator, which allows us to control the path of light. The figure here shows the schematic of the micro-ring resonator switch. The switch follows laws of constructive interference and total internal reflection. A resonant wavelength can be tuned by electric field. The electric field changes the reflective index, which allows the light to take one of the paths. For example, the blue path here shows what happens if the switch is off, that is, no electric field has been applied. However, if an electric field is applied, the resonance frequency changes such that the output is now collected at the other port, which is marked as output 1. This is shown in the red. Using the components that we just discussed along with other optoelectronic components, we propose this architecture for performing parallel reservoir computing. The delay lines used in this architecture are on-chip. Therefore, this is a completely on-chip architecture. This architecture is very similar to single-node photonic computing model that we discussed. The input layer is the same. It uses a masked input and couples it with the feedback from one of the delay lines and passes it into the modulator. However, after the modulator, a micro-ring resonator switch that we have introduced into the architecture decides whether the output of MZI goes to delay line 1 or 2 or delay line N. The delay lines can be distributed among tasks, and a particular delay line can only have states from the task assigned to this particular delay line. The output layers are again off-chip. Here are some of the parametric details of components used in our proposed architecture. We use a laser of wavelength 1550 nanometer, an MZI which has a power of 5 watt, a delay line which has a length of just 2 centimeters, and a delay of 660 picoseconds. This is also electronically tunable. And we use a photodiode with a rise time of 15 picoseconds. The delay line is specifically on chip. Now we discuss the evaluation of our architecture. We use IPCAS, which is a commercially available tool to synthesize the photonic components. We use OJER and Keras for RC simulation. OJER and Keras are Python libraries for machine learning simulations. We use Descent for power and area analysis. The benchmarks used are analog speech recognition and NARMA task. To experiment with our proposed architecture, we compare the proposed architecture in different configurations. There are 3 different configurations. We first simulated the system in a standalone configuration for one task only. Then we simulated the system with 2 tasks with equal delay times. Lastly, we simulated our system with 2 tasks but with unequal delay times. The delay times basically determine how many neurons are assigned to a single task. We could then compare the proposed architecture with other state-of-the-art architectures. Here are the results for NARMA and analog speech recognition in all 3 different configurations as simulated in our proposed architecture. For NARMA task and for analog speech recognition, we see that the standalone performance is best. However, as we go to E1 and E2, there's only a minor degradation for NARMA task, whereas for E1 and analog speech recognition, there's a major degradation. E1 is basically 50% priority to analog speech recognition task. When we give a higher priority of 60% to analog speech recognition in E2, the performance improves significantly. This is also a prime example where we can tune our architecture such that at a very less loss in performance for NARMA tasks, we gain huge performance bonus for analog speech recognition. In this table, you can see our results compared with some of the state-of-the-art architectures for reservoir computing. MRAC here, which is the 4th in our list, is basically a multi-layer reservoir computing architecture. The performance of our architecture is better compared to all other state-of-the-art architectures. This is primarily because we use a delay line which is only 2 centimeters, resulting in low propagation loss. Here we compare the size of delay lines in state-of-the-art photonic architectures with our architecture. All architectures use from 20 meters to 1.7 kilometers, whereas our proposed architecture is only using an on-chip delay line of 2 centimeter length. Here we compare our results to another architecture which uses time division multiplexing to perform jobs in parallel. Basically, in time division multiplexing architecture, a single reservoir is divided among 2 different tasks. Our proposed architecture performs a lot better than their architecture. To conclude, in this paper we propose the photonic RC architecture using multiple delay lines for parallel processing and an on-chip system. The motivation behind our work was the fact that state-of-the-art architectures were not exploiting the inbuilt parallelism in the reservoir layer while using an off-chip component in the form of a fiber spool. Our proposed architecture has components that were synthesized using photonic CAD tools, which are commercially available, which is IPCAS. The proposed architecture also provides 84% less error compared to state-of-the-art standalone architecture for NARMA tasks, Whereas for multitasking, the proposed architecture shows 80% better performance compared to an architecture that uses time division multiplexing to divide reservoir layer among different tasks. The simulations were run in Ojar and Keras. The on-chip area and power overhead of the proposed architecture due to delay lines and introduction of micro-ring resonator switch is also minimal. Thank you so much for attending my presentation. If you have any questions, please feel free to ask.
Thank you, Said, for your presentation.
Thank you.
Okay. I have a question. So,
sure.
For your prototype, is it viable? Can you how is it going to cost or something like that? Tell me more about the hardware itself.
Okay, so for the hardware itself, we don't have a physical chip at the moment. This is something that's left for the future work, obviously due to funding reasons. Also because the techniques required for the on-chip delay line that we are talking about is something that we still need to develop within our group. What we do for now for the prototyping simulations, what we do is we use the IPCS tool, which is a commercially available photonic CAD tool, and we basically take all the parameters of device physics parameters from people who have done that, and we go there, program the component as it is to get its characteristics such as power, area, and how the propagation of light through those components look like. Then we take that and integrate that into our machine learning model and run simulations based on that.
Okay. I was curious about the 2 centimeters. Why not 3, why not 4, why not 1 centimeter? Is there a reason for it?
Right. So basically what we wanted to do is we wanted to use components that have been fully tested in literature before integrating that into our system design. So the delay line that we've used is based on a prior work, and in there, the maximum delay that have been achieved is 660 picoseconds with a length of 2 centimeters. So the way they work is that you have certain gratings within the waveguide itself. By applying some electric field, you control the refractive index of the particular delay line. And based on that, you can get a certain delay due to total internal reflections and variations in refractive index. So our goal was to basically get the maximum delay that's currently possible in waveguide-based delay lines, which is 660 picoseconds. And for that, we required a 2 centimeter length. But obviously, as the device physics improve, you could obviously vary that.
Okay. We have another question from the audience. Do you expect your actual results to be close to the simulated results?
That's a good question. So what I'm familiar with is that for example, the fiber spool that I've shown in Vinegar's work, that's primarily the only work that I'm familiar with that actually builds the chip and has a very similar architecture to ours. We did simulate their model and got results that were pretty close. But I think once you integrate physical components, if there's like crosstalk or if there's error due to the component itself, obviously you'll have to modify that and see what happens there.
Okay. One last question. What would you do if you need more delay? I would say more than 600 picoseconds.
Right. So there are a few things that we can do. First is if you wanted, so we haven't tried this, but this is something that we are planning in the future, that we can have a hierarchy of delay lines and use that to basically integrate more MMR switches, have the light loop around and go back into a certain delay line, either the same one or a new one. That way you can increase the delay. A second approach is that you can add multiple reservoirs. So in one of our initial works, what we did is that we had not a similar architecture, but basically multiple reservoirs. So that uses multiple delay lines. So what happens is that once you have the modulated data come in, it passes through a delay line, and then it goes to the next delay line. It does act as a new reservoir, but since you can couple all the reservoirs together to form one big reservoir layer, or a bigger reservoir layer, so you do get an extra delay.
Okay, thank you very much. Just a final comment. I think that you have to sell your speed up from 1,700 meters to 2 centimeters. It's a real
good.
Time.
Right.
Okay,
Yeah.
thank you very much. Nice presentation.
Thank you.
And
Thank you.
this closes the section. And I don't know if someone else has a comment about all papers or about the section itself, or should we close it? Okay.
Okay, we will have a break of 5 minutes. We come back in 5 minutes.
Okay, thank you very much. Bye-bye.
Professor Gabriel Falcão, can we start?
Hi, hello. Yes, of course, we can start. Yeah. Can you hear me?
Yes.
Okay.
You can start.
Okay, so good afternoon, everybody. So for the first paper in section 6, online sharing aware thread mapping in software transactional memory, we will have the presentation from Douglas, and I propose that we can start hearing it.
Hello, I'm Douglas Pereira Pasqualin. I'm from Federal University of Pelotas, Brazil, and I'm here to present our paper where we develop a mechanism to improve the performance of software transactional memory by map threads to cores in runtime according to their memory access behavior. So, since this work focuses on the transactional memory, I will give some background on it. The idea of transactional memory is to simplify the parallel programming by replacing the use of explicit locks with atomic blocks, executing a critical section of the program as a transaction. In that case, if a transaction executes without conflicts, it will commit. A conflict happens if two threads access the same shared resource, and at last one transaction writes to this resource. Otherwise, if a conflict is detected, one of the transactions must abort, discarding all operations made inside and restart until the commit is possible. However, transactional memory has some drawbacks, mainly in high contention environments, due to high numbers of aborts. There are many works trying to improve the performance of transactional memory, more specifically transactional memory software, STMs. However, most of those works focus on the use of transactional schedulers, and the main idea is to serialize in conflict transaction. In that case, if conflicts are detected or predicted, the scheduler picks one transaction and puts on the same queue of the other, making them execute serially, avoiding new conflicts. However, our work is different. We propose to improve the performance of STM by using a technique of thread mapping based on the memory affinity between threads. We expected that this approach will improve the cache usage of the machine and thus the performance. Also, our idea is to integrate this mechanism inside the STM runtime. In that case, it will not be necessary to change the source code of the applications. Here I will give you a brief background of shareware mapping. That's the technique that we will use. More specifically, in a shareware thread mapping, threads that access often the same shared resource are mapped to cores that are close in the underlying architecture. This will improve the cache usage and the interconnections of the machine, thus improve the performance. However, we have some challenges to do that. For example, how do threads share data? In shared memory system, communication is implicitly made through shared memory areas. Also, we need to discover the memory address being accessed. We can use some external tools to discover that, but they add overhead to this application. We need to choose how to represent the affinity between threads. So the most common structure used for this purpose is a communication or sharing matrix. Here is an example of a communication matrix. Is a matrix where each pair of cells indicates the amount of affinity between pairs of threads. For example, here threads 4 and 0 access the same shared resource 9 times. On the right, we can visualize the matrix using a graphical way, where dark cells indicate more communication. Now, we will describe our mechanism called STMap to exploit shareware thread mapping inside STM. We saw that one challenge to discover the memory access behavior of application is to discover the memory address being accessed. However, on STM, we already have this information because the STM runtime needs this information too. Thus, our idea is when at least two threads have accessed the same address, the amount of communication between them is incremented and stored in a communication or shared matrix. With this resultant matrix, it's possible to calculate an optimized placement of threads to cores based on the memory access behavior of each one. Here is our proposed algorithm to discover the memory access behavior and perform thread mapping in STM. So it begins on each transactional read or write. But since we are interested in doing the thread mapping runtime, we not keep track of all accessed memory address, because it implies high overhead. Hence, we use the concept of sampling. So first we check if it's time to sample the memory address by checking for the sample interval threshold. On the next slide I will talk more about that. If it's time to sample, we first retrieve the information about the memory address being accessed, checking the numbers of previous access to it. If it's the first access to the address, we only save the current thread as share 1. In all steps, we check if it's time to calculate the new thread mapping by checking if the mapping interval is greater than a given threshold. Like the sample interval, we'll talk about it later. However, if it's the second access to the memory address, we store the current thread ID as share 2, and now we have a communication event between share 1 and share 2 position, and we update the communication matrix. The last case is if you already have 2 preview access and the current one is a third access. In that case, we need to update the communication matrix twice with the current thread ID and the 2 previous shares. And since we only keep the last 2 threads, we need to remove the oldest share and save the current one. And here is an experiment that we made in order to choose the best sample interval. We have used 8 applications from the snap benchmarks. We start with sample interval of 0. In that case, our memory address were sample. Also, we collect each communication matrix for each sample interval and calculate the mean squared error against the matrix of the sample interval 0 to verify the accuracy. That values closer to 0 are better. So based on this experiment, we choose a sample interval of 100, where we had the best trade-off between overhead and accuracy. Another threshold is the map interval, when the new thread mapping should be calculated. The map interval is based on the total of access address, not on the samples. To avoid the overhead and contention, to calculate this threshold, we only keep track of the total access address of the first thread. And based on experiments, we choose a map interval of 100,000 to trigger the thread mapping. The last part of the mechanism is how to calculate the thread mapping. So when the map interval is triggered, the communication matrix is sent to Topomatch, an open source mapping tool to generate the new thread mapping. After that, the threads are attached to cores according to the new thread mapping calculated. However, since not all applications are suitable for a shareware thread mapping, we create a heuristic that tries to predict if the application will have benefit of a new thread mapping before calculating it. The heuristic is based on the distinct address accessed of the application and the abort and commit ratios. About the methodology, STMap was implemented inside TinySTM library, which is one of the most used STM libraries. And for testing, we have used stamp benchmarks, which consist of 8 applications covering a wide range of transactional characteristics, and 2 synthetic micro benchmarks, HashMap and HeadBlack3. In this presentation, we will show the results on a Xeon machine with 96 cores, but applications were executed using 32, 64, and 96 cores. And for comparison, we executed the application using a Linux map, in that case is the default operation system scheduler with OTN intervention, scatter, in which the purpose is to reduce the memory contention, compact that shares all cache levels, and round robin, which shares only the last level of cache. Also, we use a sharing aware static approach, which consists in execute the application only to get the communication matrix using a sample interval of 0. After that, we calculate the new thread mapping using the collected matrix and re-execute the application with the calculate thread mapping. And finally, we execute applications using our STM proposal. We will start with 2 applications that are suitable for shareware mapping. We can see here that the HeadBlack3 application achieves a good performance using a static mechanism. and the online mechanism achieve equals or better performance. For example, in 96 threads. Probably using 96 threads, the application has a different sharing pattern on each execution, and only an online mechanism can adapt to this behavior. On k-means, we can see the same observations. However, on 32 threads here, the map interval was too high and the application never triggered the mechanism. Labyrinth is an example of an application that is not suitable for shareware mapping. Using the static mechanism, you can see here, we have performance loss compared to Linux, but the heuristic of STMap correctly disables the mechanism, achieving performance similar to other mechanisms and avoiding performance losses. On SSE2 is the opposite. This application is suitable for a shareware thread mapping, but the heuristic incorrectly disabled the mechanism. In that case, the performance was similar to Linux. But overall, the heuristic worked correctly for the majority of the applications. In the paper, we have more results, a total of 10 applications, and we have more details about how the heuristic works. Also, we executed the applications in Opteron Machine 2. Here is a summary of speedups compared to Linux. On the Xeon machine, STMap achieved the second best speedup, losing only for the static shareware mechanism. And on Opteron, although the general speedups were less than Xeon, STMap achieved the best speedup against all mappings with about 9%. And concluding, we presented the STMap, an online mechanism to use information about transactional operations to do the shareware thread mapping. We showed that the STM system has enough information to perform a shareware mapping, and the mechanism has low overhead, allowing us to perform operations during runtime. As far as we know, it is the first work to perform a shareware thread mapping in runtime for STM. And as a future works, we intend to improve the heuristic to disable the mechanism, since it has not worked precisely in some applications, and add data mapping too, because since it is working, we only have exploited thread mapping mechanism. And I think that's it. Thank you very much.
Okay, so thank you, Douglas, for your paper, for your presentation. I think we already have questions here in the Slack S6P1 channel. So you all feel free to join us and to leave your questions at the Slack channel. So we have a first question, which is if you had to choose a class of applications where SSA works best, which category would you choose?
Hello, so thank you for the question. Yes, we made some experiments. Stamp benchmark is good for this purpose because it has 8 applications, in which one with many characteristics different of workloads. So we observed that STMap works better when we have a low distinct address being accessed, not too many, and with high access but made inside this distinct address. And also, since we are keeping tracking of address being accessed only inside the STM, the applications need to use a lot of STM operations. If applications use only low regions of codes, of course, it will not work as expected, because it will only keep track of a part of application. I don't know if you was clear.
Did this answer your question, Ines? Okay, oh, your must be muted, but okay. So yeah, I have a couple of questions too. I suppose we still have time. Okay, so okay, this question was a little bit in line. So regarding the benchmarks that you use to generate memory access pattern plots, and how representative they were of the universe of real-life applications, which have gained more and with the currently proposed technology, and which have presented smaller gains, and if you have an idea why, I mean, can you elaborate on this?
Taking consideration the applications that we used,
Yeah. So I mean, you experimental k-means, right, and red black trees, and
for example, genome is application where we have lots of STM operations, but it's not access the same shard, is more disjoint data.
Okay.
In that case, a scatter thread mapping performs better because yes, we have lots of transaction operations, but it's not there are not lots of contention.
Okay.
In fact, one of our heuristic is one of the we saw on the presentation that we have a heuristic to predict if you should enable or not the mechanism.
Okay.
And one of the features of the heuristic is to see the abort ratio. So if the abort ratio is high, so the application is accessing a lot of shared data. So it's aborting a lot. So in that case, we enable the mechanism to do the thread mapping to accessing the shared data faster. With not keeping, not are worrying about the aborts. We only want to the applications access the shared resources faster, improve the cache usage.
Okay, got it. I think I got the idea. So this technology that you are proposing, how did it affect an average cache behavior? Did you measure that? Sorry. Did you measure that? Did you have an application? Did you have does it have an impact in cache behavior? I mean, you reallocate the way you perform your
yes, the speed up is based on that, because as we improve you put the threads close the underlying architecture, we improve the cache usage and thus the performance in the speed up. The speed up here that we show in the table is based on the cache improvements.
Okay. Well, one last question, because I have several questions but we don't have time. So yes, it's one last one. I noticed that the STMAP, right, the solution you propose, it seems to perform better for a higher number of threads, right? How would you estimate this behavior on GPU processors, and how would the distinct memory hierarchy and several memory banks, whatever, with potential conflicts impact this approach? Do you have an opinion on this?
Yeah, it's hard because I don't work with the GPU. So to be honest, I don't feel comfortable to talk about that. But you saw that about the threading increase is more likely to improve the performance. But on the ZIL machine, we have the NUMA factor higher than the Opteron. So it is impacted too. Not only the high thread numbers, but the NUMA factors. But of course, we are studying that on the further works. We are working yet on the STMAP, and we have too many things to do, and this is good.
Okay. So you have a lot of ideas and a lot of ways to proceed your work. Thank you, Douglas.
Yes.
It has been a very interesting presentation. Okay, so I suppose we are on time, so we should proceed to the next presentation. It's a paper about optically connected memory for disaggregated data centers. And the presentation will be made by George Gonzalez. I would like you to start the video, please.
Hello, my name is Jorge Gonzalez, and today I'll present our work, Optically Connected Memory for Disaggregated Data Centers. This is the summary of our work. Our motivation is the limitation in bandwidth and energy efficiency of current interconnects to disaggregate the main memory. This represents a problem for scaling memory for future data centers. Our work OCM proposes a new optically disaggregated memory to overcome that problem by studying processor performance when memory is disaggregated and by designing a silicon photonic link to sustain DDR memory. Our work showed promising results with 5.5 times better performance compared to 4 unique-based disaggregated systems and low energy overhead of 10.7%. We conclude that our work is a promising step toward main memory disaggregation. In today's agenda, first we will introduce the disaggregation concepts. Second, we will give some background of the memory interface. Then we discuss our work motivation and goals to present our optically connected memory proposal. And finally, we show the evaluation, discuss results and conclusions of our work. In HPC data centers, the gap between computing power and communication is increasing. For example, with Summit, the ranked #1 supercomputer in 2019, the communication per computation or bytes per flop ratio decreases 8 times compared to 2017. This shows that data centers require maintaining most of data inside the node for computation. To improve the compute power and efficiency, we need to increase the number of resources. However, the existing underutilization of resources and operation costs motivates to develop new architectures and new interconnect technologies to have efficient data movement in order to reduce the gap. One solution is the disaggregated approach, where instead of having a server-centric data center, we have a network of resources. The figure at the right shows a pool of resources in different racks: CPU, GPU, storage, and memory. Those resources can be allocated according to the dynamic workload to compose a disaggregated server. If we consider memory as a critical resource for computing, to disaggregate memory from the processor is a challenge, because we need a high bandwidth and reconfigurable interconnect that enables up to 10 meters distances, rack distances, considering its actual limit of a few centimeters. The conventional memory interface establishes a communication channel between processor and memory. As we can see in the single channel figure from the left, it uses a shared data bus to access 1 DRAM DIMM per time. Its physical constraints limit the number of transactions required. For example, a 64-byte cache line performs 8 times 8-byte transactions. In case we need more channels, we need to double the previous interface, for example, for a dual channel configuration. And this is difficult because we need to consider the electrical constraints such as the pin count, the associated wiring, and in data center scenarios, the rack distance. So how can we disaggregate the main memory? If memory of chip bandwidth is limited to a few centimeters, we need new technologies as photonics that provide high bandwidth, low energy, and large distances. In this figure, we estimate the number, I/O count, of the memory channels for DDR4. In the blue bar, we can see that electrical interconnects requires 1040 I/Os to sustain the DDR4 aggregated bandwidth, while a photonic interconnect will require only 2 I/Os. We can scale the number of memory channels using photonics. Prior works show that photonics is a promising solution for main memory disaggregation. However, there is no comprehensive analysis that evaluates both how a processor interacts with a disaggregated memory subsystem, executing real applications, and at the same time the sibling design to obtain relevant metrics such as energy and the number of required optical devices. Our goal in this work is to propose the optically connected memory architecture and study both processor performance with OCM and the sibling analysis for memory disaggregation. To introduce our optically connected memory, first we need a processor and DRAM DIMMs grouping channels, as we can see in the figure. For example, 2 DIMMs per channel. OCM uses state-of-the-art optical devices in its silicon photonic link. The sibling has a master controller on the processor side and endpoint controllers on the memory side. The sibling is based on micro-ring resonators or MRRs to obtain low energy and low area consumption. The sibling is also bidirectional and is composed of sublinks. The physical connection at rack distances is established with optical fibers. In addition, it is required laser sources to produce multiple wavelengths for communication. OCM uses the dense wavelength division multiplexing, or DWDM, to use the wavelengths as depicted in red, yellow, and green colors to achieve high aggregated bandwidth. In OCM, we use the same wavelength for all the RAM DIMMs in the same memory channel. Notice that with DWDM, a single fiber can carry multiple wavelengths at the same time. This figure represents the read and write operation in OCM. For example, if we need to perform an operation from CPU to the channel 1, first, the processor requests a read or write, then the electrical signals are converted to the optical domain in a process called modulation. The optical signals are propagated through the optical fiber to reach the endpoints. Then the optical signals are converted to the electrical conversion to electrical domain in a process called demodulation. And finally, if a write is required, we store data in DRAM DIMMs, or if it is a read, we load data, and we repeat the process from step 1 to 4, but this time from DIMM to CPU as a target. The memory access latency on a conventional system results of sum up the read or write latency inside the module and the controller latency. In a disaggregated system with OCM, we need to consider the time of serialization and deserialization. This is a conversion from different domains, or electrically to optical and vice versa. We also consider the signal propagation delay at rack distances. To alleviate those latencies, OCM performs parallel access to the DRAM DIMMs in the same channel and increase the sib-link usage. In that sense, OCM works in lockstep operation by splitting the cache line in all the DIMMs on the same channel. For example, a 128-byte line can be divided into DIMMs. We evaluate the system-level performance of our OCM architecture using a modified ZSIM simulator and execute two versions of SBAC, Parsec, and a graph benchmark suite. We create two memory scenarios, one without a DRAM cache and the other with a 4 GB in-package DRAM cache in the processor side. We use a multi-core processor and we compare performance with three types of interconnects. The baseline interconnect, which represents the conventional memory bus, not disaggregated, the OCM interconnect for disaggregation, and a NIC-based interconnect for disaggregate scenarios. In the sib-link evaluation, we use our custom model in our Phoenix SIM simulator, which was modified to sustain current DDR4 standards. Our results without DRAM cache, as expected, show that higher OCM latency and larger distances degrades performance. Each bar inside a group represents a different latency, where the light green at the right is 6 meters. On average, OCM is 5.5 times faster than 4G NIC-based disaggregated systems. OCM showed an average slowdown of 1.07 times with the best scenario of latency. The average slowdown is 1.78 times with the worst case scenario. In this figure, we can observe the results of a disaggregated system with OCM with DRAM cache. It shows an average slowdown of 10%, and for most of the benchmarks, OCM has less than 38% slowdown. We also observed an application, PageRank, with the URANT input graph that exhibit a speed up on both non and disaggregated scenarios, with a 20% slowdown with OCM. This figure shows the energy per bit results of the sib-link operating at 615 gigabits per second, which is the DDR4 standard. We evaluated three MRR sizes represented in three colors, blue, orange, and green. You observed that the lowest energy consumption was obtained with the 143 square micrometer rings, which is the orange one. These results allow us to determine the number of MRRs and the maximum bit rate per wavelength with DWDM. For DDR4 technology standards, we need two sib-links, each with 35 wavelengths with a bit rate of 17.6 gigabits per second. Please refer to our paper for additional details. We included more OCM architectural details in the paper, timing diagram on operation, more results in the paper about measured memory footprint, multi-thread results, multi-program results, and additional sib-link configuration. We proposed an evaluate optically connected memory, and we conclude that this new optical architecture for disaggregated memory systems is compatible with current DDR4 DRAM technology. We made 3 key observations. OCM has low energy overhead of only 10.7% compared to DDR DRAM data movement energy consumption. OCM performs 5.5 times faster than 4G NIC-based disaggregated memory, and OCM can fit the bandwidth requirements of commodity DDR4 modules. We conclude that OCM is a promising step towards future data centers with disaggregated main memory. Thank you.
Okay, so thank you, George, for the presentation. I suppose, okay, we have the video. Okay, we have questions here. Can you describe the process of modulation, demodulation using MRR in your architecture and the challenges in it?
Oh, hi, thank you for the question. The process of modulation, demodulation consists of converting the electrical signals to change the domain. So in this process, we need electronic devices to work with the optical devices. These type of devices are the main device, or the most important in the electronic side, is the SerDes controller to serialize the stream from of electrical pulses. And when we serialize the stream, we can convert to the optical domain using the MRRs. So the main constraints or challenges for converting the signal are related to the SerDes design. Actually, the SerDes devices are not that commonly used for processors or memory. One example or one proposal to include SerDes was the HMC memories, the hybrid memory cubes that already include serializers. So in the future years, we expected this to become more common to have serializers ready for designing this type of systems. And on the other side, in the side of photonics, one challenge is also have a lot of MRRs at the same integrated chip. So our work has the intention to provide the insight for the photonic designers to see what are the requirements considering the computing applications. And on the side of the computer architects, we want to provide, these are the physical constraints for having this disaggregated memory.
Okay. Okay. While we wait for more questions, maybe I can launch some questions as well. So, okay, I understand there's a huge bandwidth gain here, right? I mean, the bandwidth gain can be very high, but what about latency?
Okay, related to the latency in our work, we try to model and estimate that because as we mentioned before, the SerDes are not a common device on a processor or memory system. So one of the main latencies overheads will be related to this conversion. And the latency will be very related to that value, because this is the main objective or goal for our evaluation. We try to estimate the SerDes are in this range of latencies, how the processor will behave. And as we can see, the latencies are reasonable, and at the same time, we can improve a little the performance or hide these latencies using a DRAM cache, for example. And as the technology becomes more available, or it's more common, this latency will reduce.
Okay, okay. So we still don't have more questions. Maybe one more from my end. Actually, I find very interesting the fact that you can do parallel accesses to DRAM DIMMs, right? I mean, on the same channel. This is, I suppose, a big plus of the technology. Could you explain this a bit further? I mean, is there an area overhead or complexity implicit here? What kind of additional stuff would you need to make this work, because this seems a very strong point of the work.
Because our work is also motivated to prepare a test bed. We are working on test beds, and there's previous contributions related to connect the memory using FPGAs and a photonic test bed at the Columbia Laboratory in New York. So one of the problems or one of the challenges was how can we reduce latency more? So that's why we work with lockstep operation, because one idea at the beginning was maybe we can send the same message, because this is good for photonics to broadcast and using different wavelengths. So we perform a not that efficient data movement. We send the same data to all the electronic devices, and using additional logic, we discriminate or reject the message. So we use lockstep to not do that, to improve the system. So we are working on implement or complement this test bed using this scenario. And at the same time, we are trying to provide some additional control related to the workload, more on the OS side. This is what are we working now and what we are moving towards.
Okay, so one last question, Biggie. I need a very quick answer. Have you been testing this for machine learning applications? I mean, since they were on one of the things that people load data centers mostly with these days?
So in the scenario, at this point, we are more focused on the physical side, but in the laboratory objectives, the LRL in Columbia, yes, the objective is to work in deep learning, and we have advances in that sense.
Okay. So I think we're done. We are still on track.
Thank you.
Regarding time. Thank you, George, for your presentation. Very interesting work. So please continue. Okay, and I'll send the control back to the program chairs. Thank you.
Thank you. We come back at 1:30 in 45 minutes.
Okay.
On the western edge of Europe, where the land meets the sea and the winds carry the warm sense of Africa, there is a country of friendly and hospitable people. A country of contrasts, whose diversity is one of its greatest treasures. Of lands where nature has remained untouched and time appears to have stopped. A realm of endless plains and beaches washed by the Atlantic and caressed by the sun. Portugal, a country that needs to be deeply experienced to be understood. A country of artists whose works have made Portugal world-renowned. Its long history can be seen in its imposing castles, where we can spend the night within walls that have protected kings, caliphs, and the march of time itself. In fairy tale palaces, surrounded by enchanted forests, abundant with romantic walks and secluded areas. Where even those already in love develop new passions. But Portugal has also another facet, where the grandeur of the past and the excitement of the future live side by side. A young and welcoming nation that lives intensely 24 hours a day. A vibrant country full of color, where the sun shines all year round. In mountains mountains that can take the breath away from even the most experienced traveler. In places where the grandeur of the landscape is rivaled only by the majesty of the fauna. And even when you think you have seen everything, Portugal has something more to offer. The possibility of doing nothing. Relax and enjoy the endless beaches of a country with 850 kilometers of coastline. And after a busy day, start your evening with a great meal. Because in a country with centuries of history and some of the best wines in the world, cooking has become a highly appreciated art. Portugal is all this and much more. A marvelous and captivating country from the very first moment you arrive. A unique country that offers 1,001 things to do. Embark on an exciting journey. Take a deep breath and dive into an unforgettable experience.
many times have you left early, cancelled a meeting, or otherwise changed your plan? How many times have you said you were going, but stayed right where you were, sinking in the sand? How many times did you look at yourself from another perspective and grasp, when all was said and done, you were simply in the wrong place? Listen, we're the same size as what we see and not what we have. A man needs to see things with his own eyes, walk the world with his own feet, have his back burned by the sun and his feet blistered by the street. Which is harsher, the icy winds atop a mountain or the baking heat along the plain? There's only one way to know. Seeing this with our own eyes and not on our smartphones, flashing up images of landscapes already shared a million times, really seeing with our own gazes for just a few and sometimes far too few times. The good news is they are still here. These landscapes do persist in the three-dimensional world that we exist, and they do hold the capacity to transform us. So come, take a look, but look to see and not to show, and save it right here and here. Put the phone away and go. Once we experience distance, we understand just how much we miss our own and our homes. We can see the wood from the trees. Travel helps us flourish and grow. We need to go places we don't know to shatter that arrogance that makes us experts in what we have not seen, when we should remain humble and keen as students and just head off in discovery. In 20, 30, 40 years' time, we're going to regret what we did not do. So voyage out, let the wind blow through your sails, explore, dream and discover. Believe that that sky is going to seem that bit bluer. You must have read, when something good happens, travel to celebrate. When something bad happens, travel to forget. And when nothing happens, travel to make something happen. Keep this in your head. It's the truth. And this is the proof. And it's with us each and every day. We just have to read the signs. Because after all, we can't skip life.
Mi sembra una cosa potenzialmente interessante. All'estero. E vabbè, cambiato sarà in Senti, se non vuole andare all'estero, il candidato si farà invitare da te. Non è una roba così complicata, la manifestazione di interesse. Fuori manifestazioni di interesse, quindi la Palestina è ho parlato con direi che mi bisogna tenerli. Vi ringrazio per
Brazil is calling you. Celebrate life here.
Gli ha detto al responsabile di laboratorio che ma visto che tu c'hai le ore per fare il laboratorio.
On the western edge of Europe, where the land meets the sea and the winds carry the warm scents of Africa, there is a country of friendly and hospitable people. A country of contrasts, whose diversity is one of its greatest treasures. Of lands where nature has remained untouched and time appears to have stopped. A realm of endless plains and beaches washed by the Atlantic and caressed by the sun. Portugal, a country that needs to be deeply experienced to be understood. A country of artists whose works have made Portugal world-renowned. Its long history can be seen in its imposing castles, where we can spend a night within walls that have protected kings, caliphs, and the march of time itself. In fairy tale palaces, surrounded by enchanted forests, abundant with romantic walks and secluded areas. Where even those already in love develop new passions. But Portugal has also another facet, where the grandeur of the past and the excitement of the future live side by side. A young and welcoming nation that lives intensely 24 hours a day. A vibrant country full of color, where the sun shines all year round. In mountains that can take the breath away from even the most experienced traveler. In places where the grandeur of the landscape is rivaled only by the majesty of the fauna. And even when you think you have seen everything, Portugal has something more to offer. The possibility of doing nothing. Relax and enjoy the endless beaches of a country with 850 kilometers of coastline. And after a busy day, start your evening with a great meal. Because in a country with centuries of history and some of the best wines in the world, cooking has become a highly appreciated art. Portugal is all this and much more. A marvelous and captivating country from the very first moment you arrive. A unique country that offers 1,001 things to do. Embark on an exciting journey take a deep breath and dive into an unforgettable experience.
University of Porto sits in the top 1% of the world's universities, internationally recognized by the quality and depth of its teaching and research. As a comprehensive university, we offer courses in all study areas and all levels of higher education, from undergraduate to postgraduate programs. Reasons more than enough to be the preferred university in Portugal by national and international students. A community of more than 30,000 that choose the University of Porto to develop their career path or a research project. We stand out as the largest producer of science in Portugal, authoring 25% of all the scientific papers published every year. In our research units, you may find some of the most productive and renowned European R&D centers. Consequently, the University of Porto is a driver for innovation, helping students and researchers turn ideas into new products, services, and companies. Hundreds of startups and thousands of new jobs were created in our premises, affirming Porto as one of the most innovative regions of Europe. Moreover, all this is done in one of the most beautiful regions and cities of the world, voted as Best European Destination. The city of Porto is itself an attraction, booming with life and culture, and we at the University of Porto would welcome you with open arms.
In the 1980s, over 3 decades ago, INESCTEC's researchers were already using optical fibers for data, video, and voice transmission. And today, this technology is commonly used in our television, broadband, and telephone packages. Back then, INESCTEC was already ahead of its time, but the goal was to go even further, paving the way for innovative research and projects, using technology that only a handful of companies had access to at the time. That is how HBM Fiber Sensing was born, one of the many spin-off companies created at INESCTEC over the last 30 years, all thanks to a culture of research and work practices based on innovation and excellence. But INESCTEC's researchers focus on different areas of expertise, contributing to technological evolution, to an increase in the company's productivity, or to improve the quality of people's lives. Involved in multiple national and international projects, combining resources from the University of Porto, University of Minho, University of Trás-os-Montes and Alto Douro, the Polytechnic Institute of Porto and other institutions, INESCTEC brings together more than 900 researchers, including professors, postgraduate students, grant holders, hired researchers, technicians, and administrative services who work on building a future according to the needs of the present. For instance, the work of hundreds of researchers at INESCTEC has already made it possible to provide broadband, low-cost internet access in remote ocean areas. In the transportation area, INESCTEC's researchers have already developed solutions to improve the mobility of millions of people, such as a management tool that is vastly used by companies in the sector. Thanks to new technologies created and developed at INESCTEC, there are innovative projects and extraordinary advances in different sectors, such as aquaculture, sports, renewable energies, assembly lines that revolutionize the footwear sector in Portugal, electric mobility, industrial robotics, business reorganization and modernization, cryptography and security, hospital management or medicine, whether in the complex world of organ donation, chronic illness monitoring, or rehabilitation using the so-called serious games. INESCTEC is going through a vibrant and exciting period, offering training to young Portuguese researchers at the highest level. More than 30 years later, INESCTEC's growth is unquestionable, and so is the diversity of its scientific areas, the multiple initiatives, the scope and global impact of its activities, and the way the institution prepares people for the global market. All this was unimaginable in the distant year of 1985. 30 years have passed, and INESCTEC has, in its own right, consolidated its position in academia, in the Portuguese business fabric and society, as well as in Brazil. All that by doing research, developing technology, offering qualified training, and improving the daily lives of people in Portugal.
Venir à 20.
Professor Giovanni?
Hello.
Hi, you can start your session.
Thanks. So in this session, the first paper will be presented by Ivy Peng on memory underutilization, a paper that works on exploiting disaggregated memory in HPC infrastructures. So Ivy, are you there?
Yes, I'm here.
Okay. Hello, so you can we can start the presentation and then we will have some questions.
Hi, this is Ivy Pen for Lawrence Livermore National Laboratory. In today's talk, I'm going to introduce our research on memory underutilization on existing HPC systems. Based on that, we introduce a library to support existing HPC applications to start exploring disaggregated memory. When a user requests for a resource for a job, they have to request it at the unit of a node. It has been observed that imbalance among nodes could exist inside one job. Some nodes may use more resources than the other. However, due to the cost-grained resource allocation, the request has to be done at the peak usage. Also, different jobs may require different configurations of resources. For instance, some applications may be more compute intensive, some applications may require more memory resources. Disaggregated architecture could support different resources to be configured independently. Also, resource allocation can be done at a much finer granularity based on need. Different resources can be disaggregated, including I/O, compute, and muscle memory. In this work, we're only going to focus on disaggregated memory resource. Resource waste because the resource is requested based on the peak usage.
Just an explanation, the video is still running, but the comments are not recorded. The presenter can open his mic and talk and speak the slides.
So, Ivy, can you speak over your presentation, because we
yes,
aren't hearing the.
I suggest that, and I can.
He can open his camera and microphone, and
yes.
he can explain the slides.
Yes, yes.
And the performance will.
The presenter is here. The presenter is here. I suggest that, and I can.
Presenter is here. Yeah, it's connected. I think it's not muted, but I'm not hearing. Yes.
Evie, you are the presenter?
Yes. Either an audio issue?
Yeah, the comments are not recorded on your video. I can play the video, but you have to explain the slides. You have to open your mic and explain the slides. Presenter is here. The presenter is here.
Presenter is here. Yeah, it's connected. I think it's not muted, but I'm not hearing. So yes, for some reason we aren't hearing the audio. So let's say talk over the audio itself, so we can.
Yeah, the comments are not recorded on your video.
Yes.
I just have the video. The comments are not recorded. Evie, can you speak during the video? Okay.
Use the user4FD system call. This system call registers the memory regions where page fault handling is offloaded from the kernel to the user space. For transport over the network, we use the Mercury RPC library. The library supports several common protocols on HPC systems, including MPI, RDMA, and even TCP. When deploy this library, memory providers and clients are both deployed in one job. The memory providers will start up first and then publish information for the client side to connect to it. We evaluate the performance on an emulated disaggregated memory system. The emulation uses an existing HPC system. Each compute node has 256 GB RAM, and the cluster uses InfiniBand interconnect. The maximum local RAM that can be used for caching is so constrained that it will ensure each application will use more memory resources than that is locally available. The first step, we carried out a sensitivity study using two synthetic microbenchmarks. They have different access patterns, streaming and random. The two charts on the top, they report the sensitivity to the migration granularity. The x-axis indicate increased granularity from 4 KB up to 2 MB. By comparing these two charts, we could see that different access patterns have different optimal point in the migration granularity, and this is why it is important for our library to expose this control to the user space. The two charts on the bottom, they quantify the sensitivity to the network connectivity. They report 3 configurations that use 1, 2, and 4 memory providers. By comparing these two charts on the bottom, random access pattern actually saturate earlier than the stream access pattern. We also observe that when the network connectivity becomes too complicated, the random access pattern starts to have performance loss. Our first case study looked into graph processing workload. In this one, each process performs an independent breadth-first search on a graph. We used 4 different input graphs with up to 34 billion edges and 1 billion vertices. The first chart here reports the aggregate performance with the increased number of BFS processes. As we can see, when the number of BFS processes increases, the total performance also increases. To understand how the local memory capacity will impact the performance, we sweep 7 configurations of local memory capacity and report them in the second chart. As we can see from the second chart, this graph processing benchmark is relatively insensitive to the changes in the local memory capacity. Increasing the local memory capacity do not always bring performance improvement, and this is the one factor that we need to consider for system setup.
So let's get to some questions. Unfortunately, we could not hear all of the presentation, so maybe some of the questions will be redundant with respect to your presentation. But anyway, one question from my side while we wait for some more to come up on Slack. My question is related to the relation between your work and hardware works on implementing memory, disaggregated memory architectures. So your work does say improves the ability to program these systems, but then you need to take into account also the impact of the implementation, the underlying implementation. Can you give us some idea of how you can measure these impacts with respect to the emulated environment that you designed for these experiments?
So the current implementation we have done is based on an existing system. So apparently we do not have those specialized. Apparently, we do not have those specialized hardware, which is definitely designed to be have lower latency and higher bandwidth. But in the emulated environment, what we can do is we may be able to inject certain delay or slow down processor to kind of emulate a different ratio and different latency to quantify the sensitivity. And another, sorry, is that what you're asking? How
yes, exactly.
Environment?
Mm-hmm.
Right. So we do and we are aware of the underlying communication layer. Currently, it's more focused on portability. That's why maybe performance-wise, it may not be comparable to what a real disaggregated memory architecture or hardware will support. But the main objective of this work is really to provide a very convenient way for all existing HPC application to start exploring what will happen if you have memory constraint locally, and what access pattern or what insights you can actually provide when the hardware is ready. So it's more for getting ready for an emerging technology. So yeah, so that's the, I hope this answers your question.
Mm-hmm. Yes, it does. Another point is what can you do in terms of memory management, so of designing and testing policies to perform a better memory allocation, or on the other hand, task allocation to optimize these memory access times, given that in disaggregated memory systems there is likely to be non-uniform cost to access different memories.
Right. So the one main design principle of the library, our library, is to expose the control of evaluation policies and even allocation policies to the user space. So that's why we present it as a user space solution. We used a default ARU policy for all the experiments in this paper, but we believe that when the user or the application developer with better knowledge of the access pattern, like we show in this the comparison between BFS and Access Bench, then they can inform the library that maybe a larger local memory cache is not going to help, or a different evaluation policy would be better suited. So we provide this interface and this control that could enable the users to explore different policies, and also as a way to get ready for future disaggregated memory.
Thank you. So I don't have any other questions. So thanks, Ivy, for the presentation and for answering these questions. And we can then move to the second presentation. The second presentation will be on time-space optimization for memory-constrained DNN inference. And this will be done by Yuan Wen. So we can start the presentation. Yuan is here, so he will ask us afterwards.
Hello everyone, I'm Yuan Wen from the Trinity College Dublin. Welcome to my talk, TASO, Time and Space Optimization for Memory-Constrained DNN Inference. This is a joint work by the Trinity College Dublin and the University of Edinburgh. The convolutional neural network experienced huge success in recent years and have been increasingly deployed in many applications. Its usage covers autonomous cars, robotic systems, smartphone, virtual and mixed reality platforms, and many wearable devices. After CNN model has been trained in the lab or factory, it will be deployed to the end devices to do the job of prediction. This process is called inference. and it is generally lasts a long period of time. Comparing to the training process, the time scale of inference could be counted in days, weeks, and maybe even in years. Many of the devices running CNN model are battery-powered systems. On the one hand, they are usually resource constrained with mobile processors and small main memory sizes. This is determined by the size of the equipment and the battery capacity. On the other hand, the functionality of the application requires the model running as fast as possible and consumes memory as less as possible if you don't want to drain the battery very quickly. With the limited hardware resources, large neural network models will need to be specially optimized to meet the constraint of each device. So CNN are architecturally different, designed by experts. They share some characteristics in common. A convolutional neural network consists of an input and output layer, as well as multiple hidden layers. The hidden layers of CNN typically consist of series of convolutional layers that dominate the computation and the memory consumption. These layers chain together with one layer's output connected to the next layer's input. Each layer uses one operator. The figure gives an example of runtime and memory requirement of GoogleNet. The default way to construct CNN is to implement the neural network with a single primitive for all layers, such as direct convolution, image to row, image to column, and vinograd, shown in colored circle dot. Alternatively, we can also configure the CNN with different primitive for each layer to optimize the network towards time and memory size. The red diamond shows the minimum memory requirement, while the green rectangle presents the best performance achievable. From this figure, we can see that a mixed primitive selection is capable of providing a better performance or memory consumption. Though global optimization works well, in practice we often have to face the problem of detecting the best solution under some constraint. Take data from GoogleNet, for example. If the memory budget is 230 megabytes, we want to know what the best performance we can expect is, or the other way around. If the program requires the CNN model to be finished in 200 seconds, and to satisfy this goal, what is the minimum memory we shall spend? The goal of this paper is to answer these questions: how to achieve the best performance under a given memory budget and consume smallest memory under a given performance requirement. Our solution is constructing the CNN with carefully selected convolutional primitive for each layer. When we examine the CNN model, the execution time of the model is accumulated time of each layer. The memory requirement for the whole network is the sum of the buffer size of each layer as well. Because of the linear relationship between time and the number of layers, we model the problem by integer linear programming. Linear programming is a mathematical model that seeks to maximize or minimize the objective function subject to a linear constraint. In integer linear programming, all decision variables are constrained to be integers. IOP solver search for the solution that meets the constraint of these linear relationships, while simultaneously seeking to minimize one particular objective function. In the classic IOP formula, X represents the decision integer variables to be determined. C and B are coefficient vectors. A is a coefficient matrix, and AX less equal to B and X larger equal to 0 are the constraint. We then search for the solution X to satisfy the given constraint with the lowest cost objective function. When mapping to a problem, taking maximizing performance, for example, X is a vector of primitives selected for each layer. The objective function C is the accumulated execution time. We then search for the whole memory consumption to satisfy the given memory budget with the lowest accumulated execution time. The formula for minimizing memory consumption has a similar form. More details can be found in our paper. Here is a complete formula for minimizing execution time under given memory budget. The time of the CNN consists of execution time for all layers and the time spent on data layout transformation, because different primitive only work on particular form of data. Then we constrain the function by forcing the accumulated memory consumption under the budget. L is a group of vectors, with each vector represent a set of primitive options for a given layer, indexed by I. The vector is a one-hot vector. That means only one primitive that can be selected for the given layer. We test our method on an embedded system with ARM Cortex-A15 CPU. 57 different convolutional primitives have been used to construct CNN networks. The network we have tested in our paper include AlexNet, VGG, GoogleNet, ResNet, SqueezeNet with a dataset of ImageNet. We developed our IOP solver with POP that implemented in Python. The offline solver is performed on a desktop environment with Intel Core i7 CPU. The figure shows the execution time for running 5 networks. The first 4 bars are the performance of each network with the same primitive for all layers, while the rightmost bar shows the result of our IOP implementation. All results are shown in the form of speed up over the direct convolution, hence the metric here is the higher the better. In the experiment, our IOP solver found the fastest primitive combination. Since there is no memory constraint in this experiment, the performance of our IOP is the same as that of PBQP, which is the state-of-the-art implementation. We run the global optimization for memory footprint versus static network configuration as well. The y-axis shows the memory consumption. It is a metric of lower the better. Still, the IOP implementation outperforms all the others. The figure shows a Pareto frontier of the IOP optimal solution for primitive selection when varying the memory budget. The solution to the left of the chart optimizes the memory in detriment of the execution time. Each blue dot is an optimal solution detected by our IOP solver. Comparing to the solution given by PBQP, which has marked as point A. With the Pareto frontier information provided by our IOP solver, the configuration of point B reduces more than 2/3 of the memory consumption with a negligible performance slowdown. We observe the similar pattern in other deep neural networks as well, such as AlexNet, SqueezeNet, and VGGNet, and VGG and ResNet. The implementation of greedy, we also implemented the greedy algorithm to consider adding memory constraint to the PBQP strategy. The algorithm first tries to optimize the choice of primitive selection to obtain the shortest inference time. That is what the PBQP does. After that, if the memory footprint budget is exceeded, the primitive with the largest memory footprint will be replaced by another primitive with a smaller memory footprint but fastest among all the other remaining candidates, so that the inference time is not compromised. This process is repeated by replacing the candidate primitive until the constraint of memory budget is satisfied. We present the speed up achieved by our method against the greedy algorithm on varying memory budget constraint. We can see that when the memory budget is plentiful, both solver makes similar good decisions. While with the tightening of the memory constraint, the greedy algorithm begins to provide suboptimal solutions. This is because there are just a small set of very good solutions when the memory budget is small. In the experiment, our ILP solver reaching 8 times speed up when the budget is tight. The time cost of solving configuration is negligible. Taking largest neural network used in our experiment, for example, to solve the configuration of GoogleNet, there are 3,990 decision variables. Our solver finished the detection in 23 seconds. One thing also worth to mention is that this is an offline process and no runtime overhead would be introduced. Here we conclude our work. In this paper, we propose an approach for ahead-of-time optimization of CNN models based on integer linear programming. By selecting appropriate primitives for layers, we optimize the trade-off between computation performance and memory consumption. This strategy can be used to run any CNN on any platform with a C compiler. We evaluate our method with a range of popular ImageNet CNN architectures such as GoogleNet, AlexNet, VGG, ResNet, and SqueezeNet. On the ARM Cortex-A15 CPU, our method yields 8 times speed up compared to the greedy algorithm and capable of detecting the best trade-off between performance and memory consumption adaptively. Thank you. Hello everyone, I'm Yuanwen from the Trinity College Dublin. Welcome to my talk, TASO, Time and Space Optimization for Memory-Constrained DNN Inference. This is a joint work by the Trinity College Dublin and the University of Edinburgh.
Okay,
right.
It stopped. So
yeah.
we can have a few questions. So we have a question from Ines. Do you think an adjustment to the heuristic used in the greedy algorithm could produce similar results as the ILPs?
Not really, because it's, the ILP is finding the global optimum, and unless the greedy algorithm had all the knowledge about its the candidate's strategy, but in that way, it turns out to be an ILP like it's a solution. So the greedy-based algorithm cannot be tuned to having similar result. But maybe there's an exceptions when the budget is quite flexible. For example, there's no budget at all. With detecting the space over and over again, perhaps it can find the greedy algorithm can find some result is equally good or maybe similar, but it's not in all cases.
Okay, thanks.
Yeah.
Let's see if there are any other questions from the audience.
Yeah.
Okay, so meanwhile, I will ask one myself. So you compared with several other methods to generate the network implementation, and the ILP formulation, as more or less can be expected of let's say an optimization that looks into all the possible choices, it tends to provide better solutions. But does it tell you something about why the other methods fail in finding the solution? So that there are any, let's say, general issues with these methods, or it's just that sometimes solutions are really hidden in difficult points to reach with other methods?
Sorry. Oh, you mean compare? So where other method doesn't work, right?
Yeah.
So the the solution is kind of balance the performance and memory consumption, and this is accumulate and in an accumulated way. So for each layer, you come with different primitive convolutional primitives. Each one comes with a different performance, is a various execution time, and comes with different memory consumption. And we have to balance these two metrics at the same time. And we want to find the trade-off. So the ILP is the kinds of some mathematical tools and aiming in solving this type of problem. So we have some target function, and we have a bunch of decision variables, which in terms of the primitive itself. Each has two attribute the time and the memory. And then the ILP the function is, because it's a linear relationship between each layers to the overall performance and memory consumption. So the ILP, the mathematical tools, is able to constrain some of the variables and then optimizing towards the target function. But it's apart from that, the rest of the method is not capable of doing this. Or maybe you can do try all the combinations from the configuring the neural network in a brute force way. But it would result in the same question. But the ILP is functionally much efficient than that one.
Yeah. Thank you.
Yeah.
So thanks for the presentation and for answering our questions.
Thank you.
And we can switch to the next presentation.
Okay. Thank you.
You're welcome. The next presentation will be by Martin Johnson. It's a fast and concise parallel implementation of IECT using the Allied language. So we can start the presentation.
Hello, my name is Martin Johnson from Massey University in Auckland, New Zealand, and I'm here to present our paper about JPEG decoding using Halide. Firstly, why did we do this work? Well, there are some libraries that need to be as fast as possible. For example, linear algebra, FFTs, convolutions, and so on. And it's often thought that to get the best performance, you need to write these libraries in a low-level assembly language. However, this makes them difficult to maintain, and when a new architecture comes out, they have to be rewritten. For example, libraries often have to support SSE, AVX, AVX2, and AVX512, and that's just for the x86 architecture. So, what have we done? We have rewritten a key part of the libjpeg turbo library, which is a widely used JPEG decoder. Our implementation uses a functional domain-specific language called Halide. It's much easier to maintain than all those lines of assembler, and it turns out that it's faster too. This is what I'm going to talk about. First, I'll show you the most computationally intensive part of JPEG decoding, which is the IDCT. Then I'll show you the Halide language and how we implemented the IDCT in Halide and our performance results. Firstly, what is the IDCT? It's an inverse discrete cosine transform. The discrete cosine transform is still the way that most videos and images are encoded. The image is split into blocks that are transformed, quantized to throw away small values, and then encoded using entropy coding. For JPEGs, the block size is fixed at 8 by 8, and since you are doing lots of them, you really want these to be fast. Here's a diagram showing all the steps in the decoding of a JPEG image. From the file, the transform coefficients are obtained using Huffman decoding in a zigzag pattern. These are then multiplied by quantization coefficients. Then the IDCT gives us the original 8 by 8 block back, and the 3 color components are combined to give us 64 pixels in the image. Of these steps, the IDCT is by far the most computationally expensive. It's an n log n algorithm and needs to be applied for each row and then each column. So we need 16 8-point one-dimensional inverse transforms. The JPEG standard doesn't say what algorithm to use for the IDCT, but there are 2 common ones. They are named after their authors and are often called the LLM and the AAN methods. LLM needs more operations but is more accurate, and so it's generally known as the accurate method, while AAN is faster but less accurate and is called the fast method. The original open source JPEG library is called libjpeg, and this was written in C. A fork of libjpeg was started in 2010, and that's called libjpeg Turbo. This adds assembly language using SIMD instructions for the DCT and IDCT for many architectures. It also includes benchmarking code, which we use for our performance results. libjpeg Turbo supports all popular architectures and popular SIMD extensions. Each IDCT needs between 500 and 1,000 lines of code, and there are about 25 different implementations, with over 20,000 lines in total. Here's how the SIMD code works for an 8x8 transform. The rows of coefficients are stored in 8 vector registers, each containing 8 16-bit elements. The IDCT is performed on these 8 registers, which does 8 parallel column transforms. The registers are then transposed so the columns become rows, and the IDCT is performed again. They have to be transposed once again to put things in the correct place. So now let's talk about Halide. Halide is a domain-specific language for image processing and computational photography. It was developed at MIT and is used extensively by Google. It's how their HDR+ algorithm is implemented on their phones. It's a functional programming language, but you write it inside C++ using a generator to make native code for almost every architecture and operating system. The interesting thing about Halide is it decouples the algorithm from its implementation. You describe the algorithm using pure functions declared with the keyword func, which can then iterate over variables declared as var and using expressions. These expressions are strongly typed, and the bounds for iteration are inferred automatically. There are other features of the language like reduction domains and update functions, but we don't use them here. After you have defined your algorithm, you say how to schedule it. An algorithm will always produce the same result when given a certain input, but the schedule determines how quickly you will get that result. The important scheduling operations for us are vectorize to use the SIMD instructions, reorder schedule to rearrange for the transpose, unroll to avoid unnecessary loops, and compute at to say when to do a particular operation. Here is the Halide code for a one-dimensional 8-point IDCT transform. It uses the fast algorithm, and all the multiplies are done with constants between 1 and 2. We can use fixed point arithmetic for this. F is the input function and G is the output function. X, Y, and Z are vars declared elsewhere. The Halide code must match the available SIMD instructions so that they can be generated. Halide uses pattern matching to find valid instructions for each architecture. x86 provides 2 instructions which we can use. The first is good if we have a fixed point constant between -0.5 and +0.5, while the second works for constants between -1 and +1, but with 1 bit less precision. For ARM, there is only a single instruction, which is the same as the second x86 instruction, except it must use saturating arithmetic. These are the Halide expressions we need. I16 is a cast to a 16-bit integer, I32 a 32-bit int. So the first means multiplying 2 16-bit ints to get a 32-bit int result and then return the top 16 bits. The bottom 2 are the same, but they do rounding, and the ARM instruction must saturate the result. If we don't use these exact expressions, our code will work, but it won't vectorize well. We had to submit a patch to Halide because the pmul HRSW instruction wasn't included in the patterns, but now it is. Here's the final architecture-dependent code. First we get the integer and fractional part of the multiplier. Then for fractions less than 0.5 we use pmul HW. For fractions between 0.5 and 1 we use the doubling version. Finally we might need to add the integer part back afterwards. Here is the final generator. It performs dequantization, then calls IDCT8 dim1 to do the 1D column transforms. Then it transposes, does the 1D transform again, and transposes again, scaling to fit the 8 bits with an offset. The schedule sets the format for the buffers and then uses a hand-tuned set of compute at, vectorize, unroll, and reorder schedule calls. We had to modify the libjpeg Turbo C code to call our new Halide generated code. We made it so that we could decode a whole row of blocks instead of a single block, and we had to add some glue code to tell Halide about the buffer of blocks to decode and where to put the output. We counted the number of each instruction used by our Halide-generated code and the handwritten assembly in libjpeg Turbo. The Halide code uses fewer add and sub instructions, but more multiplies and transpose instructions. Where our code really does well is by using fewer loads. This is because we don't have to load the quantization coefficients each time. Here are the accuracy results showing the peak signal-to-noise ratio for different JPEG qualities using a test image. Our accurate method is more accurate in 8 out of 11 cases, and our fast algorithm is always better because we use more scale bits. In fact, our fast algorithm is almost as accurate as the standard accurate algorithm. Here are the performance results from Intel i7. This performance includes Huffman decoding and color conversion, and the x-axis is JPEG quality. As you increase quality, more time is spent in the Huffman decoding, so overall performance decreases. The bottom two lines, the squares, are the standard libjpeg-C implementation. The triangles are the assembly implementations, and the circles are our Halide implementations. The graph on the right shows that our code is between 5 and 15% faster than the assembly language. For ARM, the results are even better. Here our code is up to 32% faster than libjpeg Turbo. Also remember that our fast algorithm is almost as accurate as the libjpeg Turbo accurate algorithm, but is over 40% faster. These are the results for one of Intel's low-power CPUs. The Halide accurate code is 15 to 24% faster than the assembly, and the fast code is 5 to 12% faster. So in conclusion, we replaced a lot of lines of assembly with 100 lines of Halide code, which even if it was slower would be good because it's more maintainable, but it is faster and more accurate. The nice thing is that this lets you experiment much more easily with different algorithms and optimization techniques. Halide isn't appropriate for everything. It doesn't work well for sparse data or anything with complex data structures. It's best for dense 2D or 3D data, but there is a lot of that type of data around, so we think it does have many application areas outside of just image processing. Thanks for listening. I'll be on Zoom along with my co-author after the talk to answer any questions you may have.
So, thanks for the presentation. Now for the questions. Let's see if there are any questions from the audience. Okay, while we wait, I will ask a question myself. So what you mentioned that this domain-specific language focuses primarily on 2D, 3D data. So did you try to work on other application domains other than video or image processing?
I've used it for image processing a lot in the past, and the Halide people themselves have done FFTs and some linear algebra stuff with it. So people have used it, but no one's used it for something like this before. And I've used it mostly for image processing, which is what it's really targeted for.
Mm-hmm. Okay. And another question is related to the language itself. So how easy it is to put a programmer to speed in working with a domain-specific language that is?
It depends what you've done before. If you've done lots of functional programming, then it's not too hard to pick up. And it does a lot for you, so it's very concise. You can, that 100 lines of code does a lot of work, and it takes a little while to learn, but once you've figured out what to do, then you can write really fast code with it and really quickly, because it's doing a lot for you, and it's very fast, and it will automatically parallelize, and even if you have just the standard schedule, then you're going to get something that works, so you don't have to spend any time optimizing your code. You can work on the algorithm, and then afterwards you can make it faster.
Okay, I have a question here from Ines Dutra. It is arguable the difference between highlight and assembly. Could you highlight the advantage, considering that the code you have is a bit manually crafted?
So I didn't understand that. Where's the question that we
in the Slack channel?
In Slack. Yeah. Okay, well, yeah, it's not that much faster, but it's only 100 lines long instead of 20,000 lines long. So that's the advantage. If you can replace 20,000 lines of code with 100 lines, that will also produce exactly the same code for all of the same architectures. That's not a bad thing. It's much more maintainable. And the thing is that once you've got those 100 lines, then you can change the way things work, and it'll still it'll still compile to all the same architectures. So one of the things we did, we changed it so that rather than doing a transpose at the end, you do the zigzag pattern in the other direction, and you get the transpose. It means you don't have to do the transpose. And we can do that because we've got just the 100 lines of halide code, but you couldn't do that with the assembly language because you'd have to rewrite the whole thing to take out all of the transposes and all of the implementations. So that immediately makes it faster anyway. And we could experiment with different precisions and seeing how that affects the accuracy.
Thanks. I think that the advantages are quite clear, especially from the maintainability point of view, where, of course, reduction in code size. It's
yeah. Even if it was slower, it would be good, and it's faster. So
that's good also. So thank you for the presentation and for answering all these questions. And we will switch to the next presentation. So the last presentation for this session is a paper on controlling garbage collection and request admission to improve performance on function as a service applications. And it should be given by David Quaresma. David. Okay, please let's start the talk.
Hello everyone, I'm David Quaresma, a student from the Federal University of Campina Grande, also known as UFCG, and I'm your host for this talk. In today's presentation, we are going to be discussing controlling garbage collection and request admission to improve performance of FAS applications. That's a work done by me under the advisor of Daniel Farma, a professor at the Federal Institute of Alagoas, and Tiago Emanuel Pereira, another professor, but at UFCG. We are also members of the Distributed Systems Laboratory from Campina Grande, or LSD, as shortened in Portuguese. Without further ado, let's get started. Managed programming languages are programming languages that execute on top of a runtime environment. They became very popular in the cloud, especially for long-running stateful applications, and the main reason for that is because they introduce a series of benefits which makes the software development cycle easier. One of the benefits, in special, is the automatic memory management that frees the developers of the burden of managing the application memory by themselves. That's good because it reduces the software time to delivery and the risks of bugs. A popular implementation of automatic memory management is based on garbage collectors, or GC. It is well known that GC brings performance problems for cloud services, and that happens for two main reasons. One is when the threads compete for CPU, and the other is when the application threads are stopped due to GCs. As you can see in the picture, the GC might severely impact the response time of the application. The plot on the left, the one with the GC impact, shows response times values bigger than 900 milliseconds, while the one without GC impact, on the right, shows its maximum values near 140. Functions as a Service, or simply FaaS, is an instance of the cloud computing paradigm called serverless. It is a new offering of computing as a service that promises to simplify the development of applications. In this model, we have the resources managed by a cloud provider, remaining only the application logic itself at a function level. Functional replica here is also the basic level for scalability. It is also worth to mention that managed programming languages are popular here, and that differently from the previous cloud context we discussed, here in FaaS the functions are ephemeral and stateless. Due to that, the function might not live long enough to be impacted by a garbage collection. Thus, the first thing we did was to evaluate the GC impact in this FaaS context. FaaS are very popular nowadays, and there are a ton of providers, so we decided to use the AWS Lambda as template for the scope of this work. The following plot compares the performance of two scenarios. One impacted by garbage collections, we call it as standard, and it is represented with a red line, and the other not impacted by any GC. We call it just as no GC, and it is represented by a blue line. As you can see, the GC impacts the response time. At the median, it increases the response time around 6 and 9% approximately. At the percentile 99.99, it impacts even more, reaching around 24 and 33. These two ranges of values are under a confidence interval of 95%. Once verified that GC impacts FaaS applications, we evaluated and proposed a solution to eliminate the GC impact. Our solution is based on the Garbage Collector Control Interceptor, or GCI. The GCI is a request interceptor that prevents your application from being impacted by garbage collections by denying requests during those collections. So, to explain it better, let's take a look at the figure. Here we have a load balance and two replicas of some microservice having the GCI in it. Note that for the load balance, there is no GCI, only the microservice, because GCI works transparently. The first replica has the GCI and the microservice in red because the replica has an ongoing collection. Due to that, GCI will refuse any incoming request in order to avoid the garbage collection impact. So, in the following moment, we have a successful request from the second replica and a refused request from the first one. The load balance will redirect this refused request to the second replica, and then this request will be finally returned when done. This request redirection feature is quite simple to configure in Nginx load balances. Regarding GCI in the FaaS context, especially talk about the AWS Lambda focus of our work, each instance of a function only runs one request at a time. So we propose a change in the AWS autoscaler to accommodate the transient replica failures introduced by GCI. Let's see how it works in practice. Just like the previous example, the red component means that the replica is performing in GC, and thus GCI will be refusing any incoming requests. The first replica will refuse the request while the second one will be busy processing it. The autoscaler now will have to create another instance of this function, and the load balance can redirect the refused request to it, as you see in the animation. We simulated the AWS plus GCI environment, and the first thing we evaluated was the response time. As the figure shows, the ECDF is statistically similar to the one that we used to show the impact of the garbage collector in the FaaS context. That means that the GCI was successful in eliminating the garbage collector impact. The ECDF in blue represents the response time of GCI, and the red one the response without GCI. So, in the median, GCI improved the response time around 7%, and In the percentile 99.99, this improvement reached around 24 to 33%. So, as we mentioned, GCI introduces transient replica failures. In FAS, functions are scaled down automatically after a period of idleness. This period is counted by what we call the idle deadline counter. The thing is that GCI might reset this counter by refusing a request and redirecting this request to some idle function instance, as well as starting new replicas that would need to wait for that deadline to be turned down. Both situations could lead to a decrease in the resource usage efficiency. In this figure, we compare the resource usage efficiency for a set of idle deadline configurations. We noted that GCI did not impact it, but improved it instead. For an idle deadline of 30 seconds, GCI improved the efficiency by approximately 18%. For 5 minutes, GCI improved it by around 14%. Lastly, for idle deadline times greater than that, we saw no statistical difference between GCI and no GCI scenarios. I would like to thank you all for being here with me. For any questions you might ask, please don't hesitate to contact us in the SBAC-PAD Slack channel, S7-P4. We also highlight that you can email us by one of our emails as well. So that's it. Thanks again.
So thank you for the presentation. Let's see if there are questions. So while we wait for the audience to ask some questions, let me ask one myself. So in function as a service environments, one of the key challenges is the fact that the function per se can be relatively small. So overheads from added components such as the garbage collection can be significant. So what is the overhead that you get in the let's say the standard scenario? So you will when the garbage collection is not active, is there any overhead due to the fact that you are checking whether you are garbage collecting or not?
Yeah, the main thing about the GC on FAS context is that functions are ephemerals, so they might not live long enough to be impacted by GC garbage collections. But when it happens, it might increase the response time for that function because the function might stop all procedures that it is running for respond for the invocation in just to clean memory, just to perform the garbage collection procedures. So as we highlighted in the presentation, the first thing that that was not sure is that if garbage collection were really an issue for FAS context. And as we studied in the scenarios that we studied, it was an issue, and it improved the response time for around 6 and 9% for the median, and even 20 and 30% for the percentiles 99.99, which is relevant because even though you might not think that high percentiles are important to be considered, they are in some point. So that's it. The garbage collection, they impacted for the scenarios that we have evaluated considerably. Have I answered the question?
Yeah, sure. And another question. is related to the environment. No, several of so the point is you had to in some way emulate an environment that is closer to source one. So it's a proprietary environment that is so not possible to immediately replicate at a software level. So you had to collect through either black box measures or the literature information about AWS. So how difficult is it to characterize this kind of service from the point of view of the garbage collection, of course?
What do you mean, the service? You mean the Lambda, AWS Lambda?
AWS.
So in the AWS Lambda and other fast providers, we have the function itself inside a container. So the garbage collector in this context that we are studying is focusing in that part of the platform, because we know that the platform is not only the function in the container in that the function is in, right? There are other components that are programmed using a runtime environment, one language that runs on top of a runtime environment, and those other components of the functions as a service architecture structure, they are also impacted by the garbage collection in their way. But we're not interested in understand how the garbage collector would impact the fast platform in other components, but the function itself on the container level. So the way that the garbage collector might impact the function in the AWS Lambda, in the container level, it might impact in other providers as well. If they use the same function configured in the same technology of virtualization in container. But of course, there are other components inside the container that are specific for the platform that it will, how can I say, it will change how it might impact the application. So even though we were focused on a specific state case, we think that these results might be also relevant for other cases too, other auto platforms too.
Thanks. So I think there are no other questions. So I would thank you once more for providing this presentation and for answering the questions. And since this was the last presentation of this session, we can close the session and
come back after the break at 2:45. Professor Lucia.
Okay.
You can start the next session.
Yes, of course. Welcome to session 8. We will have in this session 2 papers. At first, we'll play the video, and after each video, we'll have some time for questions. Please put your questions in this Slack. So we can start. And the first paper is predicting the energy consumption of CUDA kernels using SymGrid. Douglas is here. Dora is here. Okay. You can start, please.
Dora is here, yes.
Okay, Dora, thank you.
Hello everyone, my name is Dora Buxela from India, France, and I'm pleased today to present to you my work entitled Predicting the Energy Consumption of CUDA kernels using SymGrid. In this introduction, I will try to respond to 3 key questions. First, where are we from the exascale target? Second, where are we from the 20 megawatt target? The response for these 2 questions is that we are almost halfway, thanks to the 2 Japanese supercomputers, Figago and MN3. Third, we may wonder now why we are not there yet. Well, moving from peta to exa is not only a matter of computational power. There are many technical problems, like memory, programming models, and power consumption. Power consumption is considered as the first-class constraint for achieving exascale performance and effectiveness. To tackle this challenge, many systems like the ones in the TOP 500 and GRID 500 are adopting the CPU-GPU heterogeneous architecture. Taking all into consideration, from the targets to the challenge, we try through this work to predict accurately and efficiently the energy consumption of GPUs. In our work, we rely mainly on NVIDIA GPUs. For simplicity, an NVIDIA GPU architecture is composed of several multiprocessors, SMs, and multiple levels of memory hierarchy. The execution model in NVIDIA GPUs is at the heart of its performance and scalability. CUDA, which is both the platform and the programming model, expose a high abstract view of the architecture. As we can see here in the picture, the host, the CPU, launches a kernel on the device GPU. So when the kernel is launched, a grid of blocks is generated and threads are grouped into blocks. A lot of research work has been made in predicting the performance and energy consumption of GPUs. For that, we classify them based on their followed approach. On one hand, we can find models using performance counters, whether by using linear or nonlinear statistical methods or by building visual ones. On the other hand, we can find models that rely on architecture parameters, such as the simulator-based models. Even though those models exhibit accurate results, most of them lack portability, flexibility, and requires a deep expertise of the underlying architecture. To avoid all this limitation, we propose a simple and lightweight model that relies only on one independent variable, the number of blocks. The feature selection of this variable is mainly based on our preliminary experimentation when studying the impact of execution configuration parameters on time, power, and energy consumption. As you can see here in the figures, we have the profiles, the runtime profiles of vector-add with a block size equal to 1024, where the execution time increases linearly by varying the number of blocks on 2 different GPUs. Well, if we dive deeper, we can see that this curve is stepwise, and that helps us characterize the scheduling algorithm of blocks in the GPU, which is simply round-robin scheduling. By applying a simple linear regression on the plots we saw earlier, we can predict the execution time of a CUDA kernel, as shown in equation 1. For energy consumption, it can be predicted as the sum of its dynamic energy and static energy. If we look further in equation 3, we can see that we have the introduction of 2 new parameters, EB, which is the energy dynamic energy consumption of one block, and PS, which is the static power. Both values can be obtained by the simple linear regression on the energy curve. Further, we can extend our models by taking into account the round-robin scheduling. For more details, please check the papers. Now we show a simple example to get the main idea of our modeling approach. For that, we suppose that we have a GPU with 4 SMs, a CUDA kernel with the number of blocks equal to 18. As the scheduling algorithm is round-robin, we start by calculating the number of rounds. The number of rounds here is equal to the sale of the division of the number of blocks by the number of SMs. True, it's not the reality, but we have made the abstraction that for a round, the number of blocks is equal to the number of SMs. And indeed, in this case, we have 5 rounds, as we can see here. So our models can be extended from the one that we saw earlier to the granularity of rounds. For our experimental setup, we used 2 NVIDIA GPUs, one Fermi and one Kepler, on 2 different infrastructures, and we relied on 6 different types of CUDA kernels, mainly extracted from the Rodinia benchmark suite and the CUDA SDK samples. For our measurement methodology, we used the sampling rate of 50 milliseconds on both the GPUs. We used CUDA events for profiling the execution time, and the NVIDIA SME for extracting the power ratings and other relevant metrics. Please refer to our data collection methodology in the paper. Moving now to the simulation part, we choose SimGrid to implement our models, because first, it is a versatile open source framework for developing simulator, of course, and second, because it provides already models and APIs and plugins to simulate abstract algorithms. In our work, we relied on the S4U interface to describe our application and on the energy plugin to simulate its energy consumption. Our algorithm would only necessitate 3 inputs: the number of SMs, the number of blocks, and the number of flops to be executed each round. Here we show an example of a platform file in SimGrid with calibrated values. For evaluation, we compare simulated values with real ones. Indeed, our datasets are randomly selected. More information about datasets and kernel configuration are well described in the paper. In this figure, we have the evaluation of the kernel 1 from the application pack propagation with a different number of blocks. We can see here how close the simulated and predicted and simulated and measured values are. More precisely, on the Fermi, we have a highest average relative error equal to 6.69% for runtime and 6.86% on energy. We have captured this on the vector-add kernel with the block size equal to 256. After analysis, we captured that this is mainly due to the memory bandwidth saturation. On Kepler, we reported a highest average relative error equal to 6.54% for runtime and 8.33% for energy. Those high values were reported for matrix multiplexation with a block size equal to 1024. With careful analysis, we find that those high values are mainly detected for kernels with small number of blocks, because the GPU Kepler is capable of optimizing for runtime and energy with higher number of blocks. To conclude, we start by highlighting our model strength, such as the simplicity and ease of use, only one independent parameter, the readiness to use already implemented in SimGrid, and exhibiting promising predictions on 2 different GPU architectures, and the fact that it is potentially portable across GPU generations. Indeed, we highlight as well our model limitations, like the fact that it's not applicable for all kernels, especially the ones with subroutines, because the developer doesn't know beforehand the number of blocks. The fact that we have to calibrate our simulator for each CUDA kernel, and the non-capability to highlight very easily bottlenecks. For our future works, we will explore concurrent kernels and dynamic voltage frequency scaling as energy optimization techniques. Thank you all for your attention. Hello everyone, my name is Dora Books.
Hi Dora, very good paper, very good presentation. I'm checking here if you have questions. I have some questions. Why do you think your model can be generalized for other GPU boards? You think it's generalized or portable? Portable, you use the word portable.
Yes. Okay, hello, thank you for hosting this session. It is portable because it is mainly relying on one independent parameter, which is the number of blocks. And this parameter is not related to the architecture. So the architecture, it's not really an architecture detailed parameter. And it's related mainly to CUDA programming model. So for NVIDIA GPUs, we don't think that the CUDA program model is going to change because it's working very well, except the GPU architecture, they add sometimes some cores like the tensor cores or something like that, but it's the programming model is still the same. We have a kernel which is dispatched, it's divided into blocks and it's grouped into threads. So it's the same programming model for all the generations. So we think with our approach, it can be portable. What I may add is that the scheduling algorithm, because we take into consideration the scheduling algorithm of blocks. This one, we are not sure it will be the same for all the generations, but we estimate, that's why we say potentially portable, because we estimate as it is working very well, NVIDIA won't change it so far. That's the point. So it depends on the scheduling algorithm, but I manipulated lately some new GPUs because I had access very lately to those GPUs, and I didn't see that the scheduling algorithm has changed.
Okay.
That's why I said potentially, yes.
Okay, thank you. Let me see. Okay, and I think usually the other strategies adopt performance counters to obtain these, to predict the energy consumptions, and time, and other things. Your model is much simpler. But do you think that these parameters that you use, the number of blocks, they influence the performance counters that usually are adopted to predict the energy consumption? Because you didn't use the performance counters, you used the number of blocks. The other works, I think they usually adopt performance counters. But perhaps there is a connection between number of blocks and performance counters. I don't know if you checked this or...
Yeah, okay. So yeah, in our work, we doesn't use performance counters because it is already stated in the state of art, using different statistical methods to see the correlation between power and or performance with the performance counters. So what we avoided to use those performance parameters, but we think for sure that while varying the number of blocks, it has impact on the performance counters and all that. But we didn't investigate in this, but it would be a good way to compare our model with what was presented and see how it is impacted. But we didn't do that for this work because we focused on our approach, but it is very interesting to compare and see how our approach and the number of blocks can have relation to the performance counters. Yeah, so.
Okay, Dora, thank you a lot. And so now we can go to the next video, please, Daniel. Thank you, Dora.
Thank you.
Congratulations.
Hello everyone, this is Riccardo Mancini from Scuola Superiore Sant'Anna in Pisa, and the topic of my talk is self-organizing maps. In particular, the evaluation of the performance of multiple open-source parallel implementations for multi-core CPUs and GPUs. What we are most interested in is how to achieve the best possible performance of self-organizing maps on multi-core CPUs and also in GPUs. For that, we have conducted an in-depth performance evaluation of existing open-source solutions, and we've developed SBAC-PAD, our minimalistic but fast implementation of self-organizing maps in Python that achieved a significant speed-up over alternative open-source implementations while maintaining a small code base. Before that, let's have a quick recap over self-organizing maps and existing approaches to parallel implementation. A self-organizing map is a kind of unsupervised artificial neural network that is used mainly in dimensionality reduction. Usually, neurons are organized in a 2D grid, thus reducing an input space to a 2D discretized grid, and each neuron has a number of weights equal to the dimensionality of the input space. We can imagine neurons as being a point in the input space, as if they were centroids and k-means. Being unsupervised, it does not use error backpropagation for learning, but a so-called competitive learning. During learning, the closest neuron to the input sample receives the biggest update towards the sample, as we will see in the next slide. After learning, each sample is quantized to their nearest neuron, and usually the output is shown as this colored grid that you can see on the right, where the lighter colors indicate a higher number of samples, mapping to that neuron. In our work, we only focus on the learning phase, since it's the most time-expensive part. As I was mentioning before, the classic learning algorithm works as follows. For each new sample in the input dataset, you first find the closest neuron, which we'll call best matching unit, or BMU. Then, you update the position of all neurons by a delta, that is proportional to the neuron sample distance, and a neighborhood function on the 2D grid, centered on the BMU. By doing so, the closer the neuron is to the BMU on the grid, the higher its update will be, with the BMU itself receiving the biggest update. This procedure is repeated for every sample multiple times, and this cycle on the input dataset is called an epoch. In order to make the algorithm converge, usually the width of the neighborhood function decreases at later epochs, as well as the size of the update, which is controlled by decreasing learning rate. The biggest drawback of this approach is that each neuron update is dependent on previous updates, therefore the possibilities of parallelization are limited. However, this approach may be the only one available in case new training data comes in continuously, and it also shows a faster convergence in terms of number of training epochs compared to the batch algorithms that we'll see in the next slides. To overcome the parallelization problem, the batch algorithm has been proposed. Conversely to the online algorithm we've seen earlier, neuron updates are not applied directly, but are accumulated, and only a final update is applied at the end of each epoch. The formula is shown in this slide. The main advantage of this approach is that multiple neuron updates can be computed at the same time from different samples, making the algorithm embarrassingly parallel. However, the full dataset is required in each epoch, and the number of epochs is usually higher than the online counterpart in order to achieve the same quality of results. The approach of SBAC-PAD is the very same as the batch algorithm, where all computations have been rewritten, such as to be expressed using high-level BLAS calls, where BLAS stands for Basic Linear Algebra Subroutines. By doing so, XPySum can leverage the highly optimized libraries that are available for both CPU and GPU, such as Intel Math Kernel Library and NVIDIA cuBLAS. These libraries are used from Python, using NumPy and CuPy libraries respectively. In this slide, you can see the general workflow of XPySum. From left to right, data is first loaded using NumPy. Then, for each epoch, the squared neuron weights are pre-computed, which will be used to efficiently compute the Euclidean distance between each weight and each sample. Then, input samples are processed in batches. For each batch in the epoch, the squared Euclidean distance is computed in order to find the best matching unit, and finally, numerator and the numerator of the batch formula are computed for each sample and accumulated. At the end of the epoch, the new neuron weights are computed by dividing numerator and denominator. The advantages of this high-level approach are obvious only for certain aspects. It leads to a simple and relatively small code that is easier to maintain and modify. For example, in case you need to add new features. What is less obvious is the performance gain that we obtained compared to other popular open source implementations. As we'll see briefly, the use of highly optimized libraries from hardware vendors proved beneficial in our case, compared to trying to write low-level code, other than saving a lot of development time. In this final part of the presentation, I'll show you the results of our experimental runs. All experiments were run on the same machine, with a quad-core Intel Core i7-4790K, an NVIDIA GTX 1080 Ti, and 16 GB of RAM. We tested 3 different implementations, other than our XPySum. The first one is Minisum, which is a Python-based sum implementation of the online learning algorithm. Second, it's Somokulu, which is a C++ implementation and which supports both multi-threaded execution with OpenMP and the GPU execution with CUDA. It also supports distributed execution using MPI, but this latter functionality has not been tested. Finally, we also tested an open source implementation that uses TensorFlow for GPU execution that we'll call TensorFlow Sum. For each implementation, we performed several tests on 2 different datasets. An industrial dataset regarding data center metrics for network function virtualization, and the extended MNIST dataset. All the results in the following slides are on this latter dataset, which contains 240K images of size 28 x 28 pixels, showing handwritten digits like the one reported in the footer of the slide. In our tests, every measure is the average of 5 runs, and every run was timed out at 30 minutes. As a consequence, an interrupted line in the plots marks either a timeout or a crash, specifically caused by out of memory in the only case it happened. In every plot, the dashed line represents a GPU implementation, while a continuous one a parallel CPU implementation with 4 cores and hyperthreading. Confidence intervals are shown but may not be seen. We have performed 4 different tests, increasing in each one of number of samples, of neurons, of features and of epochs, while keeping everything else fixed to the default values, which are 240K samples, 100 neurons in a 10x10 grid, 768 features and 10 epochs. In this slide on the left, we have execution time against number of samples. As expected, Minisum is the slowest, since it's using the online algorithm that is not parallelized. Its execution time goes from around 9 seconds at 30K samples to 700 seconds at the full 240K samples. Next is surprisingly the GPU version of Somokulu, running slower than its CPU counterpart. Analyzing its performance, we noticed a high load on the CPU, discovering that only part of the work was actually executed on the GPU. Also, TensorFlow Sum performs poorly on GPU. Next comes Somokulu on CPU, ranging from around 70 seconds to around 500 seconds. Both XPySum implementations run better than the rest, with the CPU version being around 7 times as fast as Somokulu, and the GPU version only 3 times as fast as its CPU counterpart. On the right plot, we have execution time against number of features. In order to obtain different number of features, images have been resized. This plot confirms the findings of the previous one, with the only exception of TensorFlow Sum that crashed when doubling the image size. In this other slide, we have the number of neurons on the left x-axis and the number of epochs on the right one. In the left plot, we can see how the TensorFlow GPU implementation manages to overtake SOMOCLU on CPU. Furthermore, XPySOM on GPU manages to get a 20 times improvement over its CPU counterpart, which is still around 7 times faster than SOMOCLU. Finally, on the right, we can see again the same results as before. In conclusion, in our work we have proposed a new implementation for self-organizing maps, which proved competitive against some other popular open source implementations. In the future, we plan to add more implementation to the evaluation and to test our implementation against other different datasets and real-world scenarios. A distributed and/or multi-GPU implementation would also be interesting, which we could then compare against the popular SOMOCLU. If you're interested in XPySOM, it's available with the GPL v3 license on GitHub at the link shown in this slide. Thank you for your attention. Have a nice day.
Hello, Ricardo.
Hi.
Thank you. Very good presentation. Let me see if you have questions. Okay. A Inês Dutra told she doesn't know if she got the explanation for SOMOCLU being faster in CPU. She is asking for you to repeat the explanation, please.
Yeah, I didn't explain that much in the presentation, but we think it's the way it's been implemented, since only certain parts are offloaded to GPU, namely the pairwise distance computation between all samples and all neurons is offloaded to GPU, while the other parts of the algorithm are still executed parallel on CPU. That was probably a design choice from some local developers, but in our scenarios, it performed worse than doing everything on GPU.
Okay, thank you. Ricardo, do you believe that testing your approach with other data sets and libraries you obtain the same quality of results?
So against different libraries, we may find libraries that are implemented in different ways. So it's always good to take to the test more libraries and more implementations. Regarding different datasets, performance-wise, it wouldn't change much. It's more about checking that our implementation works well in terms of quality of results. In our experiments, we also measured the quantization error, which was not reported in the presentation because it's a boring plot, but yeah, by comparing with different datasets, we could also test it in other scenarios. And maybe we could find some scenarios in which the SOMOCLU implementation actually goes faster on GPU than on CPU. So.
Okay. Any other questions? So we'll finish the session 8, and in some minutes we'll have another keynote speaker, Professor Christine Kirkpatrick. Okay, thank you for attendance, and thank you the authors for the presentations. Very nice presentations. See you later.
We come back in 15 minutes, 3:30. Thank you.
Hello everyone, this is Riccardo Mancini from Scuola Superiore Sant'Anna in Pisa, and the topic of my talk is self-organizing maps. In particular, the evaluation of the performance
Hi, everyone. Welcome again to the last session of the SBAC-PAD Day 2. It's my pleasure to introduce you to Christine Kirkpatrick. Christine is a specialist in something that, I mean, is very neglected sometimes when we are doing something related with parallel and distributed computing. Christine is very much concerned with data placement and data storage, how you explore opportunities for dealing with very large data. She's the director of the Supercomputing Center and responsible for all the things related to data in the Supercomputing Center in San Diego. And yeah, she's been participating of several different projects around the world. She travels to several different places, not now because now it's not possible. But I know that she travels to very many places, trying to spread the word about all of the things that she does with data and data standards and everything. So it's my great pleasure to introduce you to her. And yeah, Christine, please go ahead.
Wonderful. I'm going to share my screen. And it looks like it's showing up okay. Thank you so much for that introduction. And I'd like to also say hello from Encinitas, California, just north of San Diego, which is nearby the San Diego Supercomputer Center at the University of California, where I serve as Division Director of Research Data Services. And I am also pursuing my PhD in computer science at the University of Porto, and I want to thank my advisor, Dr. Ines Dutra. Since we can't be in Porto together, I hope you will indulge me with a few photos of what we might have experienced together. Here is the beautiful fountain that sits across from the university. This will be a very data-centric talk, especially given the backdrop of HPC and new architectures being discussed at SBAC-PAD 2020. I'll spare you a data deluge slide, but there is a very present problem where, on the one hand, researchers spend 80% of their time finding and cleaning data, getting ready to do something interesting. What is needed is to flip this ratio so that only 20% of time is spent on data wrangling and preparation, so 80% of the time can be spent on analytics and research. One of the things that I hear regularly is how difficult it is for people to find data, especially computer scientists looking for domain data sets or, quote, real-world data for testing out new algorithms and models. How can this be with so much data available? According to an article published late this summer by Melvin Bobson, we produce 10 to the 21 digital bits of information annually on Earth. At 20% growth in 350 years, data will equal the number of atoms on Earth. And just before then, it will take all current power available to sustain this production. He refers to this as the information catastrophe. There are small pockets of people who work as data scavengers, doing research on data that exists rather than on new data. There is an award called the Research Parasite Award, given annually at the Pacific Symposium on Biocomputing, to recognize scientists who study previously published data in ways not anticipated by the researchers who first generated it. My path to becoming a data person comes from a career spent in infrastructure. When someone talks about the HPC ecosystem, I work on the ecosystem part. That is everything around the supercomputer, from actual powering and cooling of the data center, to the high-speed networking, to the large-scale low latency storage, and a range of physical, experimental, and virtual servers. I work on making bleeding edge technology operational, and once commodity services are available, I move on to the next gaps. I've been involved in architecting private cloud since 2012 and started a cloud integration team in 2014 as it became obvious commercial cloud and hybrid clouds would gain in importance. Around the same time, the field of data science emerged. We had data scientists wanting to use virtual machines to scrape data, to stream in data via APIs, and to run experimental and very non-optimized algorithms. There is little guidance on how to size these jobs in the cloud. They finish or they fail, or you give up waiting. I also started to recognize requests for storage and help with cloud that were really requests to create or modify data sets. The former is the purview of research computing, but the latter is often left to informaticists and libraries. This launched me in two directions: the study of bottlenecks for experimental data science workloads and proper treatment of data. To illustrate this, I want to focus on one use case in particular that was in the pathway of analysis for several different research projects: creating a body of social media data that could be analyzed using a polystore. This is an architectural drawing of the components of a system we call awesome. And for those who don't use that term, polystore is just a compact way of saying we use several types of databases together. So it's important to be able to have a raw data store and then put that into other formats, including an SQL database that is easy for users to query, a graph database, and Solr for text analysis and other technologies as they come up. One thing to note is that we have to make all of this work in the cloud, even though not all components are cloud native. In other words, we're using components optimized for client-server architectures. This is more often the case than not. Researchers use the tools they are used to or the ones their graduate students chose and can't be constantly starting over. I want to draw your attention to one piece of the system in particular, the ingestion piece that collects tweets from the Twitter API and puts them into a database. Just to connect this to a few scientific drivers, let me back up a moment. One of the most important collections for developing and refining techniques for event detection and analysis is our work with Twitter data. As fruit flies are to biologists, so are tweets to social scientists. This is an older example, but still my favorite. One computer science team uses Twitter streams to tweak event detection algorithms and methods. During the last election, a postdoc got an alert of an event that included the keywords Trump and ice cream. He thought it meant his program was broken, but he really did detect an event between a Trump supporter and women in hijabs at an ice cream parlor almost a day before the news picked it up. You can see one of the original tweets above. Below is showing that nothing was there on Google related to that news item. And then here is the news item a day later. Another domain I work with is public health. That community usually relies on what they call surveillance systems to detect if infections are up or down. With COVID news dominating our lives, many of us are now more familiar with these terms than you might have been only 6 months ago. With a surveillance system, for example, for HIV infections, current data might mean using 1-year-old data. We created a pilot where they could use social media to explore behavioral trends with much newer data. This is our case study published in early 2020. We were asked to create a new Twitter collection feed that collected just tweets using #PrEP and #condom. This is because certain high-risk groups wanted to see if there were, or rather, they wanted to see if among these high-risk groups, if there were trends related to taking or not taking antiretroviral drugs that suppress HIV and how that related to condom use. Sometimes we see things in data collection before any of the researchers would notice and ask for adjustment. In this case, our programmer caught that because APIs, the Twitter's API only matched on partial and not whole word, that he was not just picking up #condom, but everything that started with CONDOM. 1% of the Twitter feed can be enough of an example or enough of a sample if you pick the right keywords. But here we were picking up anyone tweeting about condos in Portuguese. I'd asked our collaborators how they'd wanted us to keep track of the parameters we're changing. I imagined only our programmer knew how to recreate the exact data set he'd assembled for their study. And no one really ever had opinions on what they'd like us to do with provenance. I finally asked the programmer to keep track of the changes in a text file located with the data. This is still inadequate, but far better than nothing. And here's just a quick view of if you're in Porto, hanging out at the train station. Basically, any direction is a nice view. It's typical to get a request for a subset of data related to a few key hashtags, such as the election or a health epidemic. This is also how I get interns started on special projects. Nancy Carlson at SDSC works on classification of profiles using emojis, for example. One approach to a research plan might be to say, give me 6 months of the 1% feed and put it in a Postgres database. And my expectation is that that could be ready by the afternoon or the next day so she could get started. But it was taking us quite a long time to ingest raw data, even on the same 10 gig network. The average ingest time was taking 43 to 67 minutes for every 1 hour of tweets. So to get that 6-month sample would take 5.5 months. This kind of problem leads to sizing down the sample, which is not ideal. And worse, it became apparent that the Twitter data contained duplicates that would cause the ingestion to fail. So 5.5 months was a best case scenario. The data scientists I collaborate with had a myriad of slow areas and pain points, and their solution was always, or suggestion was always, to throw hardware at it. You know, I should find a GPU cluster and I should re-architect the cloud to allow for dedicated SSDs on instances. That if hardware didn't work, then they would be happy to look at their software. And honestly, I wasn't opposed to adding to either suggestion, but it's not as simple as it sounds to just throw hardware at the problem. And we weren't really sure if GPUs would help. The dedicated SSD was intriguing, but because you have to allocate an entire physical resource, if your cloud instance only needs 100 gigs of that SSD, you're still going to use up the whole terabyte, or whatever the smallest increment that they're available in, which only grows. So we built up a very large collection of tweets. We encountered issues storing directly in a database. Some databases can't keep up with streaming data. Other times the database has issues and ingestion fails. And because we're using polystores, it's important to store the data in a raw format. And especially if the database can't keep up or ingestion is failing, you need an interim place so that you can go back and restart that ingestion. Many researchers still use open source and SQL databases, especially for exploring the data. I'm one myself, because proprietary and big data platforms are out of reach, even with research funding. In one case, we've been using a graph database that the open source version, is not easy to manage, but to move that to HP Vertica was a few $100,000 US, and that obviously wasn't going to fit into a research budget. So I embarked on an experiment to isolate the pain point and look for architectural approaches for speed up. I decided to keep this as generic as possible. I took a Postgres database and used an ingestion script that utilized Twitter's official developer schema. I used improvements already identified, such as using a RAM disk for the instance handling ingestion. Here are the main cloud instances and the sizes needed to create Nancy's project database. We know that cloud optimized applications built for the cloud work a lot better than anything invented in the 90s for client server architectures. So I quickly moved to that portion of the process. The literature on Postgres talked a lot about the underlying file system, so this is where I started. Cloud is confounding for isolated experiments because of all the shared infrastructure. Whereas on commercial cloud, this relationship couldn't be studied easily, I had access to the system logs for the shared infrastructure. We use Ceph block storage for SDSC cloud compute. What I found was a mismatch between the time format used by Ceph and my ingestion logs. When I got it all reconciled, which on its own is not easy to do between my scripts and the Ceph logs, it only confounded me more. And here you can see in white are the number of minutes of individual jobs. In the interest of time, I won't describe the rest in detail, but suffice it to say, statistically, these spikes did not correlate to a predictable impact on performance. I turned back to the data itself. Tweets are fairly uniform, but I didn't want to assume anything. Having looked at the data characteristics and finding them to be homogeneous, I looked at pre-processing. By stepping through the process, we uncovered one bug. Heron was introducing duplicate keys. By moving to a simpler API, new files didn't have these anymore, but using historic tweets would still have issues. Now I was even further from getting my data science intern to work on tweet classification, and even from my second project of speeding up ingestion. Now I was just wanting processing to not fail. Spurred by the annoyance of ingestion failing from duplicate tweets, I decided to sidestep using the tweet ID as the unique key. I believe this was used by the scientists who split users and tweets into two tables for easy joins. With the development schema and all of that in one table, that issue was moot. I modified the ingestion script to use an auto-incrementing integer, and to my delight, it sped up ingestion by 3 times or a little bit more, which was very exciting, but that still meant 6 weeks to ingest 6 months of data. With that change, I also noticed that one of the hypotheses from the data scientists was right. Ingestion is slightly slower as the database size grows, as you can see here, but not enough to be a concern. I'm hopeful I can find more ways to speed this up and or other techniques that will become more accessible over time. So far of the pain points I've examined where I've been asked to throw hardware at it, I have yet to find a true cloud architecture solution. I found another juicy issue with 30 simultaneous queries to an Apache Solr database. My colleagues were sure if we put the index on SSDs that the queries wouldn't hang. As the researcher was walking me through how to reproduce it, he wound his way to the thing that hangs, and for the first time saw it display a Java error related to a bug in his web UI. But after he fixes that, I'm hopeful I can help him speed things up more. Studying these bottlenecks, especially in the cloud and including their shared components, really showed me how important it is to have some standards in data collection so that data can not only be integrated, but also so that it could be subjected to machine learning for insights that my brain can't readily see in a graph. In traditional HPC, these sorts of bottlenecks might be approached via benchmarking and performance tuning. A group that emerged over the past 2 years that is worth watching, if not contributing to, is MLPerf, soon to be renamed ML Commons. It's a group of 73 companies and 10 universities working together to build fair and useful benchmarks for measuring training and inference performance of machine learning hardware, software, and services. Aside from being used for purchasing decisions, it allows for fair comparisons of different approaches. And here you can see the results submitted by various companies and institutions relating to the times that it took to run specific benchmarks on different types of processors and accelerators. There is a brand new working group co-chaired by Jeffrey Fox, Tony Hay, and J.N. Thalangalam related to benchmarks for research software, which I especially recommend. What still seems to be missing, whether it be cloud specific or distributed computing, is end-to-end benchmarks. For example, in that one workload that I walked you through, even though the major bottleneck wasn't related to the file system, there was a lot of variability and more to study there. I do think that my colleagues who want to try dedicated SSDs attached to cloud instances suggest something worth trying, but how am I to keep track of experiments that I run myself and make them useful to others? There is also the issue of, as more loads move to the cloud, fewer and fewer people have access to look at the full stack. Yes, there are ways to look deeper, such as CloudTrace from Google, but that is only designed to let you see across your entire application. On a commercial platform, a computer engineer is never going to get the storage logs or the underlying shared systems the jobs are running on. Cloud providers have massive capacity, especially due to the resilience of their architectures, where they can just leave old hardware running until it dies. It's not clear that efficiency is a key driver for providers. Another reason is it takes cooperation to see inside the containers as well as the shared systems. With some of our collaborators at SDSC, they run a program like Zabbix, but even so, it takes work to integrate all of the logs to look across at end-to-end performance. Forgive me with the liberties I've taken with how I've arranged this graphic at the bottom, but stay with me. Here are the various things that I could be looking at to discover areas of bottlenecks and performance gains. At the hardware level, that can include things that are low level, like traffic as reported by the network card, or higher level, such as performance from the Ceph layer that manages storage. And then there's the cloud layer, which in my environment includes OpenStack. And OpenStack is not one thing, but many components, from Keystone that does authentication to Nova that manages the actual compute. There are various places that could impact performance as well. In the case of hardware in the cloud layer, most scientists don't have any visibility to either of those layers, especially when you're working on commercial cloud. But even so, there are privacy and security reasons for not sharing those logs widely. Even of the things that one can control, there is still a lot of variability in places to integrate across to get a complete picture of performance. This can be from the choices one makes about operating system parameters to the way the containers are being built, or even the platform being used for the container build. And then of course, anything that is custom, especially scripts. In my Twitter workflow example, the ingestion scripts weren't even keeping track of time. In fact, they weren't even writing a log. They were just reporting results to the screen. What I have described to you is loosely thought of as one system. For SDSC Cloud, it does all reside in the same place. I work on other experiments such as the National Science Foundation and Schmidt Foundation funded Open Storage Network. This attempts to address the issue that every research project needs to define its own storage fabric. We've created an affordable architecture for deploying storage at the edge, near where research groups are creating data that needs to be shared with other collaborators. So we're very careful to say it's active data, not the working data that just comes off the device, but active data that needs to be shared and not archival data. It is helpful for teams who cannot gain access to a collaborator's university network, as the Open Storage Network pod sits outside in the Science DMZ and on a high-speed network. Another area for interest in end-to-end benchmarking is to understand when it's better to compute at the edge rather than send up to the cloud or have something waiting in an HPC queue. One of our collaborators using the Open Storage Network processes massive amounts of IoT data. Rather than replicate the entire data set to where the user has compute cycles, it makes sense to offer a place for a user to query, gain a slice of data that can be served up on a cloud instance, such as SDSC Cloud, all initiated from a web interface. And over time, it's hoped that more sophisticated models will integrate other priorities such as privacy. For example, in IoT or other data related to smart cities, there's often sensitive information about individuals. Research and model creation is often just about aggregation though. What if edge computing could process sensitive data and the aggregate information is all that was passed on to a larger level or stored on commercial cloud? Which brings me back to why this is a data-centric talk and not just about architectures and increasing performance issues. To do proper end-to-end benchmarking and open tracing of issues requires data that can be integrated from across all of these different sources. It requires having any plan, something far short of a standard, of how to capture and store this data. So in the example workflow that I showed you, just making the decision to keep track of time in UTC is simple but fundamental. When I originally got hold of the Ceph logs loaded onto our Grafana server and started to do quick comparisons and look for correlations, there was nothing to save me from forgetting that it logs in local time, or at least that's the way the logs are presented in the central logging system. Without data standards, biomedical science would have been greatly hindered. However, computer science persists without general advice for regular programmers on what sort of metadata to capture in a log file and suggested best practices. If you work in the field of chemistry, you can go to fairsharing.org and see the 87 standards and policies that are documented and available in the field. And that's the graphic here to the right. Some of these standards make or break analysis. For example, I'm part of the Metabolomics Workbench and work with the standard RefMet for ways of finding and describing metabolites. Similarly, in the geosciences, to say a field contains location coordinates could narrow it down to at least 3 things. Someone who hasn't worked with geospatial data may think that latitude and longitude is standardized. By ensuring that your data uses data standards, you make it possible for others to find and correlate your data across fields of study. And last but not least, consider embedding schema.org standards so that your data is structured. One side effect is that it can be indexed by the Google dataset search. Maybe someone will win a data parasite award using your data. Another area where a lack of data focus shows up in resource usability is in registered data repositories. For example, if I'm a biomedical researcher, I can go to re3data.org and find several potential data repositories on a given topic. But as a computer scientist, it is much more built up knowledge that tells me where to go for data, or I'm stuck creating my own. One shining example of this in computer science though, and that is registered on re3data.org is OpenML, and then of course also UC Irvine's machine learning repository. But we as computer scientists don't practice research data management as an integral part of our research workflow, at least not in the same way that biomedical scientists do. What GitHub is to code, we need for data. Another area where computer scientists lack in data resources is the easy ability to find appropriate ontologies. And in this context, I just mean ontology as a way of organizing your nomenclature. This is one of the key ways that data can be made to be machine readable. Some of you may use this, the graphic at the left, in your application work with biomedical researchers. It's a beautiful website called BioPortal that catalogs, among other things, ontologies. And here's an example of human disease ontology. One of the powerful things about this tool is being able to see across all of the ontologies and where a term from one has been mapped in another. And this is especially important for mapping between languages. And here I mean linguistic languages, where one term can equal 6 nuanced terms in another language. For example, I've been told there are several words in German that map to fewer words in English to describe mountain and hills. While there isn't a BioPortal equivalent for computer science, there is some work to draw on, but it doesn't go into enough detail or has uneven detail. So here is on the right is a detail from the CSO, the Computer Science Ontology from Salatino et al. If I search for cloud, it comes up with a decent amount of things under it. The portion on virtual machines is very helpful. But when I get to cloud providers, it only lists Amazon EC2. Something like CSO needs the support of the community and continuous updating to be useful in all areas of the field. But if the community does not see the value or need, then it will be difficult to have something that others value or need. CSO is a resource that I could in theory give to programmers to ensure that they are writing log output, that data is labeled appropriately with metadata that can be looked up and mapped between CSO and other ontologies. These sorts of reasons led to the establishment of FAIR and its 15 guiding principles. And in this time, I mean FAIR in all caps as an acronym. It's a sticky term that means do the right things with your data so others can find and reuse it. So many presentations only go into what this acronym means and don't say enough about how you'd actually implement these things, that it's sometimes a frustration when someone brings up a FAIR slide. So don't let me frustrate you and stick with me. I lead the coordination office for GoFair US. I'm motivated to help with the issue of increasing amounts of data that are not easy to utilize or reuse. In particular, I subscribe to the idea that many of society's challenges could be improved with what we could discover in data that is already available. The work of GoFair in particular centers around the idea of machine actionable data. While many of you may not be steeped in or deeply interested in the guiding FAIR principles, I would guess that you would be motivated to have the data that has been produced in the world ready to feed into AI. While the idea of making data so that a machine can read it might sound intuitive, many efforts to standardize data that have come before have focused on what is needed for humans and approaches that are very human intensive, therefore expensive, therefore only done on a small subset of the world's data. This is a detail from inside the Lavaria Lello bookstore, crawling with people at all times and rumored to be one of the inspirations for Hogwarts in J.K. Rowling's Harry Potter series. I hope my Porto colleagues aren't horrified. I know this is a tourist attraction, but it's a wonderful place. There are practical ways to contribute to more machine actionable data, and they start with small steps. They don't even have to rely on the changed actions for research faculty. For example, by including new skill sets and slight changes to best practices for research computing staff, data can be born FAIR so that it does not need to go through a curation process before other computer scientists run their algorithms against it. Some of these steps might actually save time and not be a fight to include. Since I manage a team of research computing people, I have thought about what things that they are uniquely positioned to do. So for example, in the use case I described with Twitter data, they should be able to associate basic metadata with the new data stores they create and to assign unique identifiers. This graphic on the bottom shows an example of how one could assign temporary PIDs to a data set as it changes over time, so that one could reproduce the work by associating the version of the data set with the publication. And once the research has concluded, the data set could receive an official DOI. There's open source software for extracting some metadata. For example, Clouder that comes from NCSA at the University of Illinois is wonderful for extracting metadata from images. And sometimes simply understanding that there are other resources to build off of rather than recreate something is useful. I remember early in my career having a program built by one student employee and then being confronted by the student that followed him asking, did you know that Andy put all of his variables in Dutch? Now, for those of you tuning in who speak Dutch, this would not be a problem for you, but at our university in California, it did make debugging very difficult. And the same is the case for the data we produce, even if it seems innocuous, such as the processing times from using an API or ingesting data into a database. Someone might want to reuse that later. I started out this talk referencing the information catastrophe. Let me illustrate a small example, again, going back to the Twitter ingestion piece of that workflow. Just making that one change from using the tweet ID to using an auto-incrementing integer over 1 year would save about 315 euros in cloud credits and power costs. So just imagine all of the hidden costs in the computing that we do and what we might discover if we were able to feed our performance data through AI. In closing, I'd like to challenge all of you to consider if you are creating computer data, or rather data about computing that is machine readable, that you use some kind of documented metadata and that it conforms to some standards of simple things like the recording of time or keeping a log at all. Consider contributing to community efforts such as ML Commons or perhaps other ones yet to be started. And above all, I hope you have stopped a moment to think about the data and what the data need to be of equal importance on its own, and not just to think about how it's tumbled and polished and reconfigured by computation. And forgive the random inclusion of these beautiful sardines and equally beautiful serving dishes. Aside from ways I hope you all feel motivated to help change the face of data, especially in computer science, once this is all over, I encourage you to go to Porto, and in addition to consuming pork, to try a real sardine. In closing, I leave you with this picture, and I know I don't know how to say this word right because I'm a computer science student and have not learned Portuguese yet, but it's a Rebelo boat on the Douro River. If you have any questions, I will be in Slack, and you can also reach out to me at this email address or on Twitter at SuperChristineK.
Thank you very much, Christine. I hope everyone enjoyed. That was a very nice talk about a very challenging problem. Let me see if we have some questions here in Slack. No questions yet, but I have lots of questions to you, actually. I know that this problem of organizing data and having everything in the storage and everyone can consume the data, and then you can utilize this data to do some parallel processing or distributed, etc., is a very, very old problem, actually. When people use it to work with grid computing, this problem happened as well. Like, for example, where should I place some, for example, data from physics to be able to consume that data faster and do the processing faster, etc. So why do you think that all of the approaches that, you know, the people that are working with data nowadays will be better than something that was in the past? I mean, people have been trying to organize these things, you know, I know that there are several initiatives in some domains, like the medical domain, image domain, geosciences, as you explained. But how do you think that these new things will solve the problem that we have from many years?
Sure, I think that, well, and let me say, preface that this is a controversial thing to say if we were at a data conference and not at a computer science computation-centric conference, but things have come before that have failed, or you could say not taken off, such as the semantic web is probably the best example. And I think why it hasn't been, why that wasn't successful in particular is all of the work it required on the part of the person producing data. So what I think will be revolutionary this time around with what some describe as building the data net, is that we need to get to the places that produce the data, to the proprietary software attached to instruments, to the things that we create, and those people need to change their practices slightly so that some data can be born fair. We're also seeing prevalence of something called the fair data point, and I didn't include that just for time, but I think this is already shown to prove successful for COVID, for organizing COVID data. So there's this thing called the Virus Outbreak Data Network, and it's being adopted in Africa. And the idea is that you don't have to put your data somewhere. So as a physicist, you don't have to send your data somewhere, that instead you leave your data where it is, and alongside it, you put up a fair data point that advertises that you have data there. You might not want to give everyone access to that data. So you might only publish metadata about what's there, and maybe you publish some summary data. And this is what they're doing in Africa with these fair data points at different places around a country, maybe a rural clinic, or it could be a health ministry, to provide real-time data in aggregate about how many cases they have. I do think that over time we will see, just as we had the search engines come and figure out how to index text across the web, we're going to see more useful tools do that for data, and that people will leave their data in place and do much less of this trying to build data lakes and put everything together. And that just as it is something we take for granted, being able to set a Google alert, for example, to look for news on your name or on something that you're tracking, you can have algorithms that are constantly looking for data that is of interest to your research. And because of better described data, we can build neural networks that know that even if you haven't supplied specific variables, that'll say, oh, you said that you were interested in mountains. I see some data about hills. Let me also suggest that to you.
Okay, thank you. I have another question. So you mentioned specific data about computer science. And you said that there is already some initial ontology to categorize computer science knowledge or whatever this is. So what's the importance of using this ontology or information about computer science for parallel and distributed systems?
Well, and now I wish I would have gone into detail on that one slide that showed Ceph performance. We take for granted that things are standardized. So if I want to compare different data about reads per minute or writes per minute, those aren't always called the same things across different logs. And so you can't just easily collect all of the logs for your job and line these things up and see, quickly correlate one process to where Ceph is reporting one thing, but maybe the actual storage cluster in its most low level software is reporting another.
Right. I don't know if you see the Slack channel. We have here some kind of comments and a question from Lucia. How do you see the relation between big data and HPC? Usually those groups did not belong to the same research group. Even the conferences are not the same and were not until now. The benchmarks to evaluate supercomputers do not take account big data application, etc.
Yes, thank you for saying that. It's an important observation as well as a question. And I will just be candid with you that even at a supercomputer center where I work, it is not, especially in the early days of data science, right when big data was coined as a term, the traditional HPC people were not very interested in it. It was not interesting to them, right? Because I've heard some describe it that HPC is like a sawmill, and people bring their trees and then they send them through and boards come out the other side. And so this idea that they would care about what was happening with these boards that came out the other side or change what they were doing just seemed kind of foreign, that's not really what they're set up to do. But what I'm seeing is that whereas HPC has been extremely successful at eking out every kind of performance gain by analyzing and controlling every portion of a job and the software versions and just everything you could think of, and is very efficient. A lot of the software that we use for big data applications is still evolving. In fact, it's that overused metaphor of trying to build a plane and fly it at the same time is how it feels to work on some of these experimental computer science projects. For example, that Polystore architecture I showed you, one of the Polystores we were using, the only one that was built for big data, was something that was under development as a research project. So, but I guess I'm a bit off track. I do see these two things coming together. One very important place of crossover is cloud bursting, as well as the use of containers on HPC. This has brought a bit of the mix of the environments that had been adopted by big data, and I don't mean big data in volume, big data more in heterogeneity. And so we're seeing a lot more crossover. And I think just the types of problems that people have that bring them to HPC tend to be things of scale. And so I do see more embracing of problems of scale in HPC, but it is still an issue that people are interested in cores and how many cores and what kinds of processors, and this will always be a conflict, I think, between HPC and data and big data groups.
I think this discussion is very interesting because yeah, the problems are very different. I mean, from one community and from the other. Actually, in this conference, we saw, I mean, at least I watched many talks about trying to solve machine learning problems and, convolutional neural networks, deep neural networks, and, matrix multiplication that are involved in the kernel of these, all of these processes of neural networks. But I didn't see, at least from the works that I watched, I didn't see people talking about, this very huge, important problem that is how shall I process all these gigabytes of data that is coming from everywhere and is, heterogeneous, as you were saying. How shall I handle this data? So yeah, I think this is a very important topic, and yeah, there are several people that have been working on this for now, I think, yeah.
Well, I do think that this is a current need that people have. I know at the West Big Data Innovation Hub, which sounds like a place you could would be a clearinghouse for data. As soon as we were established, one of our earliest questions we would get over and over is, I need some data sets to try out with my machine learning algorithms. And I would point them at UC Irvine and they'd say, yes, we've used all those. I need some more. People are hungry for data, and it's very hard to find good training data.
Yeah, true. Okay, I think there are no more questions. Does anyone in the audience want to ask some more questions? I can't see anything in Slack.
Everyone's ready for a glass of port, I think. I better not have one because it's only 9:15 in the morning here. That might raise eyebrows.
Okay, so yeah, it seems there are no more questions. So Christine, thank you very much for your talk. That was very nice. It was very nice to see you again also. So this session then closes the day. And I hope you are all here tomorrow for day 3. Tomorrow we are going to announce in the end of the conference, we are going to announce the best paper award. Yeah, I'll see you. Thank you very much for all the speakers and all the chairs and everyone that spoke this today. And thank you, Christine.
Thank you so much.
Bye, everyone.
Bye.
See you tomorrow.
University of Porto sits in the top 1% of the world's universities, internationally recognized by the quality and depth of its teaching and research. As a comprehensive university, we offer courses in all study areas and all levels of higher education, from undergraduate to postgraduate programs. Reasons more than enough to be the preferred university in Portugal by national and international students. A community of more than 30,000 that choose the University of Porto to develop their career path or a research project. We stand out as the largest producer of science in Portugal, authoring 25% of all the scientific papers published every year. In our research units, you may find some of the most productive and renowned European R&D centers. Consequently, the University of Porto is a driver for innovation, helping students and researchers turn ideas into new products, services, and companies. Hundreds of startups and thousands of new jobs were created in our premises, confirming Porto as one of the most innovative regions of Europe. Moreover, all this is done in one of the most beautiful regions and cities of the world, voted as Best European Destination. The city of Porto is itself an and culture, and we at the University of Porto would welcome you with open arms.
In the 1980s, over 3 decades ago, INESCTEC's researchers were already using optical fibers for data, video, and voice transmission. And today, this technology is commonly used in our television, broadband, and telephone packages. Back then, INESCTEC was already ahead of its time, but the goal was to go even further, paving the way for innovative research and projects, using technology that only a handful of companies had access to at the time. That is how HBM Fiber Sensing was born, one of the many spin-off companies created at INESCTEC over the last 30 years, all thanks to a culture of research and work practices based on innovation and excellence. But INESCTEC's researchers focus on different areas of expertise, contributing to technological evolution, to an increase in the company's productivity, or to improve the quality of people's lives. Involved in multiple national and international projects, combining resources from the University of Porto, University of Minho, University of Trás-os-Montes and Alto Douro, the Polytechnic Institute of Porto and other institutions, INESCTEC brings together more than 900 researchers, including professors, postgraduate students, grant holders, hired researchers, technicians, and administrative services who work on building a future according to the needs of the present. For instance, the work of hundreds of researchers at INESCTEC has already made it possible to provide broadband, low-cost internet access in remote ocean areas. In the transportation area, INESCTEC's researchers have already developed solutions to improve the mobility of millions of people, such as a management tool that is vastly used by companies in the sector. Thanks to new technologies created and developed at INESCTEC, there are innovative projects and extraordinary advances in different sectors, such as aquaculture, sports, renewable energies, assembly lines that revolutionize the footwear sector in Portugal, electric mobility, industrial robotics, business reorganization and modernization, cryptography and security, hospital management or medicine, whether in the complex world of organ donation, chronic illness monitoring, or rehabilitation using the so-called serious games. INESCTEC is going through a vibrant and exciting period, offering training to young Portuguese researchers at the